Hello, everyone. I'm glad you could all join us today. My name is Ben Escobedo, and I am the Senior Market Development Person for Shure in the Pro sector. I have the privilege of being able to support our users in location audio, Broadway, theater, broadcast, live sound, and recording applications. I want to give a big thank you to Frank and Local 52, as well as Peter at Gotham for helping set this event up. This seminar will touch on many topics from Shure's full 8-hour wireless masterclass, however we will jump around as necessary. While we are using mostly Shure gear to demonstrate various topics today, many of these concepts apply to all wireless microphones, regardless of manufacturer. In this session, we will cover many topics regarding RF, and at the end, we all should be able to describe the operating principles of radio transmission, describe the attributes and advantages of digital RF systems, position antennas for best results, perform a scan and identify interference, and correctly design RF systems with coordination tools and techniques.
So, with all that being said, we're in the digital realm right now, and we talked about that's kind of where everything is. But in reality, this is all waves, and the waves are analog. So it's what we're doing with the waves that make it digital. There's no such thing as like a digital wave. It's just everything in life is a wave, right? The spectrum of what we can hear is a frequency, what we can see is a frequency, analog, digital, wireless, those are frequencies. Waves are all around us at all times, and it matters what frequency they're at and how we work with them, which defines what type of wave they are. Waves that are visible light are not dissimilar from waves that are RF, so we'll talk about that. It is electromagnetic radiation. Basically, waves are special in RF because they don't need a medium for them to go through. For example, if I was in outer space and I was screaming, nobody could hear me because there's no atmosphere for my sound to travel through. But if I had a radio and a Shure ADX1, it would work just fine because they don't need a medium to go through. Audio and voice requires molecules in the air to carry that quality of sound to go through. And that's what makes RF special. With that being said, as you know, RF can penetrate certain objects and is blocked by others, and we'll talk a little bit about that. And of course, that gets really much interesting when we're talking about sets and different things and costumes and all that. Wavelengths is what we measure our sound or waves in, RF waves. And from peak to peak is typically what we're looking for. And it's wavelength of one full cycle, and the amplitude is how strong it is. So we'll talk different modulation schemes and whatnot, but when we're talking about the frequency or what megahertz your wireless is running, typically here we're working with 470 up to about 608 or 616, and we'll talk more about that. But this is your kind of your amplitude and your frequency are the two major things that you can change with RF. As we get farther away, of course, your amplitude can decrease. You'd expect it to because you don't have as much energy. But if we're using an FM system or a digital system, the frequency is, of course, very important. The main systems here, you hear these terms VHF, UHF, Wi-Fi. VHF is your kind of lower frequencies. Here in the US, about 174 to 216 megahertz. Most professional wireless systems are going to be UHF, though, and there's some reasons for that. UHF is the best bang for your buck as far as power, manageable antenna length, and battery life, so antenna sizes as well. Our VHF systems work well, but they are susceptible to external interference sources, such as microwave ovens and other things. The antennas are also pretty long. If you ever remember, some of the cars back in the 70s, right? Like a big American V8 car, you have the antenna on it, it's about this tall. Well, that's tuned for the VHF or 88 megahertz or 90 megahertz and so forth. If you look at some of our offerings for antennas, our VHF antennas are yay tall. And of course that is okay, but you don't want to put an antenna this big on an actor, right? That's not really fly. So UHF is where we play around for the most part with a recent repack and everything, 470 up to 608, up to 614 with some exceptions. And then we have other frequencies that are higher, like Wi-Fi, 2.4, 5.8 gig, even 6 gig now. These are great, except they're super crowded with all kinds of consumer devices. Wi-Fi devices are ubiquitous, and it's great from a manufacturing perspective because we can make one unit that works everywhere, almost everywhere in the world, with some exceptions. The problem with Wi-Fi is that it's so polluted. It's just a gamble. You never know if it's going to work or not. So it may work great one day and the next not, or somebody installs a Nest thermostat or something and everything falls apart. Right? It's not unheard of. It does happen quite a bit. So the other issue, and we'll discuss this more, but Wi-Fi devices 2.4 and 5 gig, the wavelengths are smaller and shorter, and therefore they don't penetrate as well. So as far as better penetration, the lower the frequency, the better penetration, but also the longer antenna. So this right here, this UHF is a sweet spot, and why all these cell phone companies and all the broadcasters have been using UHF for years, because you get a great bang for your buck as far as power and transmission distance, great battery life, manageable antenna length. All of those things kind of align in the sweet spot for UHF, and it's here to stay. UHF is still pretty much, in my professional opinion, where most professional users are using wireless, and it will remain that way. How we do that may change a little bit, but UHF is where it's at. It's all math. We don't have to worry about this. So. I'm an English major. So wavelengths across the electromagnetic spectrum. I was discussing this because it's just, think of it all, everything in life is a wave, everything. So no matter how fast the wave is or how many wavelengths there are, makes it result in one of these types of things. And I'm sure you've heard of all of these, right? The radio, microwave, infrared, visible spectrum, ultraviolet, X-ray, and even radiation gamma rays. Those are all wavelengths, no matter how many cycles and how fast these waves are going. And two of these we can actually experience from a human perspective with the visible spectrum as well as the audible spectrum as well. So it's 20 hertz to 20,000 hertz typically when you're born, and lose some of that as we get older. But all that stuff is a wave, and we can experience two out of those, and the rest of them maybe can some heat or something. But this is all waves, and it's just all around us at all times. It's how we harness them and how we use them. So this is a good one, how obstacles affect the wireless signal. So wavelengths smaller than the object are blocked. And I was just talking about earlier, Wi-Fi has a very small wavelength, right? Their 2.4 is much faster and smaller wavelengths than a VHF or UHF system. So if we have a metal obstacle here and the wavelength is larger than it, it'll go around. But if it's smaller, it will be blocked by that obstacle. We'll go into another scenario here. Wavelengths larger than the object are not blocked. So if the wavelength itself and the physical distance of it or the metal obstacle, it can go around that sometimes, depending on how large it is. So the larger the wavelength, the better penetration you will have. Again, UHF and VHF specifically are going to perform better than 2.4 in this instance. This is not unlike maybe some gap in a set or some sort of fence, or you can think of a million different examples about an opening. Will the wavelength go through? Well, yes. If the opening is yay big and the wavelength is smaller than that opening, it will go through. So there's kind of a give and take there of physical, can I fit this wavelength in this hole or this passage through this medium? And then also metal wavelengths larger than the opening are blocked or reflected. And we'll talk a lot about this. A lot of things can come back and bounce off. So we'll talk about this more in detail, but wireless transmitter, not unlike the one in my back pocket here, we'd like it to go directly to the receiver antennas, and that does happen sometimes, but in reality, it's going to probably not go through my body. It's going to ricochet off this back wall and off the top and bounce all around the room and then eventually find its way back to the receiver. So you got to, just because it's not line of sight doesn't mean it won't work. Line of sight is always preferred, but it does take the roundabout way of getting there, which does add some time or a little bit of latency as far as the transmission is concerned, which can affect your operation of your system. But just think about that, anytime you're having two antennas in the same plane in the same direction, it's going to be the best, but sometimes it just takes the long way around the mulberry bush or whatever. those are kind of the RF basics as far as it, but let's talk a little bit about what's happening here today. And when I say today, we're talking the last couple of years. 2017, 2019, we had the last changes of RF. And we discussed briefly beachfront property and broadcasters taking the spectrum for themselves and FCC auctions. And not only in the US, but worldwide, this has been going on where we've been getting squeezed out. And it's tough for us because, manufacturers and users of gear, nobody's asking for less wireless, right? Everybody's asking for more. And, we used to, back, not unlike 15, 20 years ago, when it first started, we had frequencies all the way up in the 700s, almost the 806 megahertz or so. And then, we lost in 2009 the 700 megahertz, and then recently we lost most of the 600 megahertz, and we're getting continually pushed into smaller and smaller areas where productions and events are still asking for large channels and amounts of wireless and such. So it's a constant challenge from us to make best use of this spectrum with the reliability that everybody wants. People just think of a microphone and it just works, right? And well, yeah, but there's things that you can do to make it better or make it more reliable or redundant, if you will. There's some things that Axient can do, and there's things that basic frequency coordination and things that you can kind of hedge your bets and just give yourself the best chance of not having a dropout, which of course is catastrophic. This crazy chart here kind of shows you from 300 kilohertz all the way up to 500 gigahertz, like what's happening. And a lot of people say, well, why are you using UHF? Can't you just use another frequency? What about 8 gig or 9 gig or whatever? And what I talked about earlier, the higher up in frequency you go, the less penetration you get, the less distance you get, the more power you need to kind of raise to get the same amount of distance. So there are systems out there that do operate in 6 gig or 7 gig, but they're great line of sight, maybe good for camera hops or spoken head like in front of a camera, but I wouldn't trust them to go around a bunch of set pieces or through walls, or if the actor turns their back or something, that could be an issue. So this is the whole spectrum here of like all the stuff that's happening. And if you remember anything, more distance as you go down in frequency with a larger antenna, and as you go up in frequency, smaller antenna, less distance, more power required to go the same amount of feet. Looking at the UHF bands here, of all this mess, we are kind of focused right in this little pocket, and that's what we have left to use. And it's actually gotten less than this. Again, here in the US, 470 up to about 608 contiguous. There's a little slice you can use from 614 to 616 called the guard band. But that's it. As far as other technologies go currently in the US, we have the VHF systems like ULXD and some others. UHF, which are a lot of systems from Shure, QLX, BLX, SLXD, Axient Digital. And then there's these little interesting slices here in the 900 megahertz. There are 2 different bands on the 900 that are open for use. One is called the ISM band. This one's lower 900 meg. The issue with this one is everything can run on it, like Wi-Fi, like kids' toys, garage door openers, all that stuff. So it's like the Wild West, and with mixed results, obviously. There is also the STL band, if you're familiar with that, with a Part 74 license from the FCC. You can use the STL band, which is about 941 through 960, and we make some gear that operates in there like Axient Digital. The nice part about the STL band is that the local kid down the block at the bar band can't go to Guitar Center and buy the stuff off the shelf. You need the license to get it. So if you're operating an STL and you do have the appropriate license, you enjoy protections just of the fact that people just aren't really operating there. And you can get kind of exclusivity in that range if you're so inclined. Now you may be saying, all right, well, 941 through 960, that's less than 20 megahertz, right? That's not great, Well, 20 megahertz with nobody else in it, when a modern digital system like Axient can get well over 20 channels in that space. We could do about 17 channels in one 6 megahertz, so 6 times 3, you're almost looking at like 60 channels, and that's in regular mode, not even high density. So there's some nice things that you could enjoy with the STL band if it comes to that. What a lot of users, depending on where you're at or where you're operating, the STL band is maybe the only way of doing it. Like we have the Super Bowl coming up here in a couple weeks, and they're definitely taking advantage of the STL band and some other frequency ranges that are usually not permitted for public consumption, including 900 megahertz STL, and there's some 1.4 gigahertz, 1400 megahertz, which is called the AvTrack band. With special permission, you can use the AvTrack band, which is normally reserved for flight communications for experimental aircraft and stuff like that, like government business. And with special permission, you can use wireless systems in there. But obviously, you can't just use them anytime you want because of reasons. You can't interfere with aircraft and all that. And then the other things we have on the higher end of the spectrum, DECT is in your 1.9 gigahertz. And there are some devices that use DECT. We have some DECT devices in the Shure portfolio in the conferencing line, like MXW Wireless. The Real Bolero system and others are in that DECT frequency. And if you're unfamiliar, DECT in yesteryear, way back in the 90s and stuff, and 80s, we had Uniden and Panasonic cordless phones in your house when you had out of line, and the DECT was designed for those telephones, for like cordless phones around your house. When this technology came to fruition, that was right on the cusp of everybody getting a cell phone in their pocket at Radio Shack or whatever, so that kind of fizzled out. But what Shure and other manufacturers have done with the DECT frequencies is used them in new and exciting ways to get wireless working there. It's a little bit less in frequency than the 2.4, so you get a little bit better range than 2.4. However, the maximum amount of systems is limited compared to UHF. And furthermore, the latency is also an issue. With modern performance wireless, we've got to keep it under 5 milliseconds at the most. Most modern digital wirelesses are like 2 to 3. With a comm system like Bolero or others, it doesn't really matter. Or a conference system where you have a gooseneck microphone wireless on the table, 14 milliseconds is okay, and that's fine. But on a stage with in-ear monitors and live performance, not really great for live stuff. So that's where the DECT is currently. It does have its applications, but typically in a low latency professional wireless, it's not predominantly the standard. And then we discussed Wi-Fi, the 2.4 and the 5 gig, low latency, but quite unpredictable. We never know what's going to happen. It could work one day, maybe not the next, depending, because everybody and their associate has Wi-Fi devices everywhere. And it could be great, and then it could not be great. So those are things to keep in track of. I talked a little bit when we opened up the conversation that these are what's happening now. In future, we're not only Shure, but Sennheiser and others are looking at newer technologies called WiMAS, which is kind of a newer, or probably the next generation of wireless. Right now, in the US and worldwide, typically we can only occupy 200 kilohertz or 0.2 megahertz of a frequency to use one channel of wireless. What WiMAS promises is putting multiple channels of wireless in a larger block. So you can say, instead of using that 200 kilohertz, I'm going to use 1 megahertz or 6 megahertz, which is equal to one TV station. And I'm going to put X number of channels in there. And then you could do cool stuff like, do I want high quality audio or do I want low latency audio? Do I need redundancy? And you kind of can move those sliders around to satisfy those needs. The biggest challenge is, and this is not super top secret, there's white papers on it and things right now that you can research. But the main challenge is convincing the regulatory bodies that we are allowed to use this and that we should be using this. Because right now they're like, well, if you take up more than 200 kilohertz, it's not allowed. And but if you can make the argument, well, we'll take up more than 200 kilohertz, but we can use more wireless in the same amount of space. And that's well, that's good for everybody. On the flip side of that argument is that if you're only running 1 or 2 channels of wireless and you take up a whole meg, you're wasting spectrum now versus using traditional wireless. So for this to happen, us and even our competitors are kind of banding together trying to convince the regulatory agencies that, hey, we want to do this in the future and that this will be cool and this will help everybody out. And this may be the only way forward to do large scale events and other things as we move forward with digital technology. It really is kind of the next frontier that's really being looked at versus where we're at now. I will say where we're at now is pretty exciting as well. We're doing some stuff with the technology and the limitations that analog wireless, we're far surpassed that. And unlike other technologies that use digital, like your cell phone or whatever else, wireless is like almost magic because it has to work the first time. You don't get a chance to ask for the data again. It's got to be low latency and reliable with good battery life and a small form factor that the talent doesn't complain about. It's almost magic that it works at all because we're cramming all that stuff into like little things like our ADX1M micro body pack, which you may have seen or may even have a few, or even stuff like the Q5X player mics, you know. These guys, the bendies, and we're putting all that technology inside of this. It's phenomenal. With 2 millisecond latency, it's crazy. Anyway, I digress. To understand digital, I guess we gotta talk about analog. Any questions so far?
How is the WiMAP, the previous thing we were talking about, different from like spread spectrum?
It's very similar to spread spectrum. It just uses different secret sauce behind the scenes to do that. It basically is like that, yeah.
Open source secret sauce? Or is
Nope. You know, we have a certain way that we're looking at that, and so the other competition has a way that they're looking at it. Just similar as like a Sennheiser doesn't work with a Shure, doesn't work with electro-digital. They all talk a little differently behind the scenes, but you know, at the end of the day, you're like, I want X amount of spectrum and I can use X amount of wireless microphones. And how that all works is still being hashed out because obviously it's not a final product yet, but proof of concept's there.
what will happen when the Shure block meets the electro block and they're on the same?
Well, same thing as wireless. More specifically, the question should be what happens when a single carrier of old school digital goes in that block? What happens? Does the whole thing fall apart? Does it have redundancy? These are all great questions. And as I mentioned earlier, the main pushback is that if I'm only using a couple of channels, is this going to be advantageous? And like, am I wasting all this extra spectrum that somebody else could be using to just use one or two links on my set? So analog RF transmission is kind of the predecessor of the modern digital, but there are plenty of applications where analog is still viable. Most notably in-ear monitors because of low latency currently, and others where analog is still reigns supreme, but those are becoming fewer and far in between than the modern digital. There's just so many benefits of digital versus analog that if you're shopping for a new wireless system, there are just really limited reasons to stick with analog than the digital. And you know, sound qualities, efficiency, ease of coordination, all that stuff, digital really reigns supreme. But in order to understand how the digital works, we got to talk a little bit about analog and still how it is and how it came to be. This applies typically across all stuff, even from like your FM radio of yesteryear in the car or any manufacturer stuff. So we have a carrier signal set to a transmitting frequency, whatever, 500 megahertz, so pick a number. And we put a signal, audio, video, typically in our case it's audio, over that modulating signal. And then the modulating signal alters the carrier signal. And we, instead of having a spike or a static spike, we kind of do things with it. And that's the whole gist of this conversation is we're going to be doing things with those waves, whether it's analog or digital. So, kind of an example here, this carrier is at 470 megahertz. May not be too good here in New York on the public safety band, of course, but we're going to use frequency modulation, put a audio signal over that FM, and then we're going to result with this. So as you can see on the chart, we have the basic non-modulated carrier signal at the top, and then the bottom, the modulated signal is going to look like that. Because we're using frequency modulation, we're not changing the amplitude. The wave's height stays the same, but we're kind of wiggling back and forth like a slinky, what the FM or the wave is altering the signal. So the different types of modulation for analog, you have a carrier signal, your baseband signal, which is what you kind of want to put through there, and then your amplitude modulation, your frequency modulation, and your phase modulation. AM is like your AM radio, FM radio, of course, and then phase modulation, we're doing things where we're altering the phase at certain points in time. Typically, most modern wireless systems are FM. Because Steely Dan says no static at all, FM definitely has advantages over AM concerning wireless microphones. In fact, I think hard pressed to find an AM professional wireless microphone, I think, this year. But AM was first, and it was easier to implement. What we're doing here with the AM is instead of changing the frequency, we're changing the height of the wave. But why you get a lot of static with AM is like you go under a bridge or something and your signal gets lowered for a split second, you get a little dropout, you get a little static, a little of that. And that's what the problem is with AM. So you can get some, lesser quality audio, limited bandwidth, and definitely susceptibility to noise. And nobody wants that with what we're doing, right? So that's kind of, AM is what it is, but not really leaned upon as much as FM. Here's an AM signal. As you can see, the frequency remains constant on the scope on the bottom portion, but the height of the wave gets modulated. And that's how AM works. Here it is in real time. Ooh, so. And as you can see, it directly is proportional to what the audio is trying to get passed through of what the waveform looks like. Phase modulation is something to know about because it's not really commonly used in analog, but it is widely used in digital, and we definitely take advantage of this in digital stuff. So as you can see, everything is kind of going along normally, and then clip, we got like a phase kind of a thing going on. Some analog systems use phase modulation to carry other data like battery life and battery telemetry through the wave. And with digital, we can kind of just encode that in the bit stream, which is super cool. And then the daddy of them all is the frequency modulation. This one here has so many other applications besides just great quality audio in the analog domain. But FM radio, analog TV audio, synthesizers, sound cards, all that stuff is based around FM modulation. So instead of relying on the amplitude or the height of the wave, we're relying on the frequency. So we're changing it, and if the signal fades out or it gets taller or smaller, that really doesn't affect it. Pardon me. So here's an FM signal. And you can see the height of the wave remains constant, but the bottom portion here is kind of like a slinky again, moving back and forth depending on what we're trying to pass through. An unmodulated FM carrier signal, if I turned on an analog wireless and I didn't have any audio passing through it, it would look like the chart on the left. This is a carrier signal with nothing passing through. And is that whatever frequency, F0 is the frequency moniker, that is whatever frequency you're tuned to. When I say, hey, tune me to 518, that would be what it looks like. When I'm actually passing audio or content through it and modulating it, this is what it looks like on the right. And historically, you'll see some little chop at the top, but again, the magic number is 200 kilohertz in the US from the FCC, and in Europe, the ETSI, which is like the ETSI, which is like the FCC of Europe. They only allow 200 kilohertz per wireless carrier, and that 200 kilohertz would be measured from here to here, so you have 100 on each side of the center that would be allowable to work with. And that's the limitation, whether it's analog or digital, and that has been a limitation for many years now. With analog, there's some things that we have to do to ensure a good signal, and it's probably important to know these just because you can understand the benefits of digital by understanding what these are, because digital doesn't require this stuff to work, where analog, it would be almost unusable without it. So there's a couple things. There's always some noise present in analog systems. If we think about noise in general, if we take a scope or a measurement device, there's all RF noise around us at all times. So there's that going on. There's also the signal of the transmitter may have a little noise. There's some noise built into the receiver or the parts in the transmitter. So like as good as you can possibly make it with the best quality components, there's still noise and stuff. And we gotta work with that and overcome that. So we also have the noise reduction, what we call emphasis equalization, not unlike using a mixing console and kind of cutting and boosting frequencies. There's also some dynamic range implications as far as like, how loud and how soft can you convey a signal with analog. Digital is way better in that aspect, but we do all these things basically on the front end, on the transmitter. We process the audio, then we pass it to the RF block, we send it through the air, and then we undo all that stuff that we did on the back end. And there's two different really kind of things that analog requires to make it work. So the first is called pre-emphasis and de-emphasis. And this isn't just a Shure thing, this is everybody's does this. Basically what we're doing is we're juicing the high end, sending it through the link, and then undoing it on the other end. And if we didn't do this, there would be some significant frequency or treble roll-off that you would encounter. So most modern wireless, I'd say all modern wireless systems typically do this, and they boost that, juice the high end, put it through the RF, pass it to the air, and then undo it on the receiver side. And also, in addition to the equalization, or the pre-emphasis and de-emphasis, as it's called, there was something which is, often used as like, compander. The digital has no compander, or compander free. Compander is almost like a bad word, right? Well, not necessarily. It's required really if you want that that great dynamic range that you can get out of a system. Pardon me. The reason why we need companding is that I mentioned there's a noise floor all around us at all times, and the link that you can get through the noise floor may be only 50 dB of variance through the audio, but we really want to get at least 100 dB of actual audio range or dynamic range. So how do we do this? Well, we compress it, then we send it through the link, and then we expand it or uncompress it on the other end. So the term compander comes from compressor and expander, and we do that on the front end and the back end. This is where a little bit of that secret sauce conversation comes in as well. Why like a Shure system, if you did it on an electro receiver, probably wouldn't sound quite right, or an electro transmitter on a Sennheiser receiver may not sound exactly right, even on the same frequency. It's because the way this is accomplished is a little different per manufacturer. So there is a little bit of secret sauce there. Not saying you won't hear any audio, you probably will, but it's not going to sound as good as if you have the matching components on each end, because you're basically want to undo exactly what you did on the front end, on the back end, for it to sound good. Make sense? So those two things, the pre-emphasis and de-emphasis, and then the compander and expander, those are done in the audio process. Then we transmit it through the FM link, we receive it, and we undo all that stuff on the other end. The other things that your requirement in a modern analog system, besides frequency multiplying and down conversion, but the other one's squelch. And the squelch, if you ever played around with a radio or a CB radio, that noise floor that's around us all the time, if you just left that gate open at all times, you would hear a blast of static through your system. And some wireless systems that are analog are notorious for this. When you turn off the transmitter, you hear a blast of static. Well, it's a combination of like the squelch or that noise gate getting triggered and being left open or improperly set, or you're on a frequency that is in use. Everything's great when the transmitter's on, but the battery dies or the talent kills the transmitter, and all of a sudden you're hearing all that coming through the system. That's a squelch setting. Squelch is like a noise gate to eliminate getting that RF noise floor. Improperly set, the squelch, if you set it too high, it's like a gate that's hard to open and your range will be reduced. You won't get as much distance. With digital systems, there's no need for squelch. It either works or it doesn't. So there's no need, you're never going to get a blast of static through your system, which is what squelch is trying to avoid. And that's another inherent benefit of digital. All right, circling way back to when we started, we talked a little bit about bouncing around the room and how that works with transmitters. We want the signal to go directly from the transmitter to the antenna. That doesn't always happen. In fact, it often doesn't happen. And the reason why there are two antennas in all modern wireless systems, digital or analog, is to combat what we call multipath interference. Multipath interference happens when I have a transmitter, not unlike this one here, and I want it to go directly to my antenna here, but maybe it goes and ricochets off that wall over here and comes back in. And then the direct signal also goes at the same time, and that one comes a little bit later because it takes a little bit of time to go there and back. And if it happens to be just 180 degrees out of phase, you have a phase cancellation, and that would mean you would have a dropout at that moment in time. This is normal behavior for all wireless systems. It happens. It's just physics. You can't really prevent this. What you can do is you can add one or more antennas with different ways to help mitigate that phenomenon. So, for example, if antenna A is getting whacked with both the direct and an indirect signal, then maybe antenna B will be better, and you'll have a strong signal on B. Now we're going to go through kind of a little bit down the rabbit hole of different techniques of how this is accomplished internally. Kind of a geeky thing, but it's interesting to see. Pardon me. Because there are different ways of doing it, and some cost more money, and that's why some systems are more expensive and considered more reliable than others. But let's take a quick look at some of the things that different manufacturers, including Shure, Sennheiser, Electro, whoever makes wireless, are implementing these ways. Again, the most simplest way of doing it is putting two antennas with a passive combiner. Think of like a cable TV Y splitter, right? You could do that with both antennas through a passive combiner, have one single receiver tuned to 500 megahertz or whatever it may be, and then you have it right there. This is not true diversity, and you also run the risk of hitting both antennas at the same time, and they could be out of phase. So it's better than not having a single antenna, but it's not quite a good way of doing it. And in fact, most systems don't use passive combining for this reason. And it's also one of the reasons why we would probably recommend against passive combining, or using it with caution if you're trying to cover on the other end, like two different areas of a set, if you will. Like, maybe you have a next room antenna and an antenna at your cart, and you want to split them to get better coverage. That's fine. But if there's ever a chance where the transmitter hits both antennas at the same time, then you can run into problems with that, and that's an issue. We'll talk a little bit more about that in the later section. But this is something to be aware of. This is one way of doing it, but maybe not the best. Another one's called predictive antenna switching diversity, and there's a lot of systems out there that do it. One in our portfolio is ULXD or QLXD. The advantage of this one here is that it's a little bit less costly to make because we only need one receiver that actually receives that frequency in the box. So if it's one channel of wireless tuned to 500 megahertz, I can put one radio in there at 500 megahertz to catch it. And then how this works is that there's a switch on the antenna. So is it antenna A or antenna B? So how it works is that if antenna A is going along, and all of a sudden the computer inside sees that signal falling, and it's like, whoa, you're going to hit 0 pretty soon, I better switch over. It'll switch over to B. The disadvantage is that it has no idea if B is better than A. Like, B could be completely disconnected. So, it's predictive. It's saying, it's better, I'm about to hit the wall, I'm just going to go to the other antenna, but it may not even be connected at all, or it could be even worse. So that's where predictive antennas switching diversity could get a little bit of a bad rap, and not quite as robust as other techniques like true diversity or true digital diversity. A receiver switching diversity here, also known as a true diversity setup from Shure or other manufacturers, uses more hardware in the box. So instead of switching predictively on antenna A or antenna B, we are actually using two receivers tuned to the same frequency. So if it's 500 megahertz, it's 500 and 500, and then we have full visibility if antenna B is better than A before we make the switch. So it's not just jumping blind off a cliff. We know that B is definitely going to be better than A, and we're going to switch over to that antenna. And this switching happens so fast, there's no break in the audio. It's like seamless, and it does it constantly. Excuse me. And in fact, a good quality system, analog true diversity system, if it's set up properly, should be switching pretty often to A and B. If it's leaning on one antenna at all times, then it means it's favoring that antenna, and maybe the other antenna isn't quite in the right spot, in my opinion. Not saying it's wrong, but it's just like maybe I'm closer to the A antenna, or the talent's closer to the A, and it's going to be leaning on A because A is a little bit stronger. But it doesn't mean that A couldn't have a phase cancellation due to multipath, and then B needs to be in the picture. So having those antennas kind of be equal is really the setup. So that's a receiver combining diversity. And there's also the audio combiner here, which kind of takes both of those receivers and makes a selection for you. Now, switching over to the digital realm, we do true digital diversity is what our marketing team calls Axient Digital. But what's really cool about this is that we're not switching between the two antennas at all. There's a radio on each antenna at all times. For example, on this box here in front of me, you can see that on channel number 4, for example, that there's two radios here, and it's on a bad frequency right now, but in this box for 4 channels, there are 8 radios. So every channel in the normal 4-channel setup gets 2 radios, one for antenna A and one for antenna B. So how this all works is that it's not switching between them, but it's kind of summing them together in the digital domain. So for example, we're really trying to get the data from the both lineups here. Let's see. So each one of these, signals is getting transmitted through the air. In digital, we're not really using the actual physical wave as the audio. We're passing ones and zeros through it like a bit stream. And A and B should be identical or pretty close to it. So what we're doing instead of switching between it is we're saying, oh, hey, was that a 1? And antenna B is like, yeah, that was a 1. And was that a 0? Was that a 0? And we're doing that really, really, really fast. And if something happens to A and it gets some wonky data, the computer can say, well, we're just going to not pay attention to that right now. So we're using both antennas at all times to get the bit stream that is intended. And there's a little bit of error correction in there. It can make up a little bit of that audio for a very short amount of time. If it was a long time, we wouldn't need performers, right? But so the sum of error correction kind of assembles that data together on those two bit streams for the best amount of data. So it's kind of like true diversity, but there's no switching going on. In fact, it's a little bit more robust. It's a lot more robust than true diversity because it doesn't really matter the antenna lengths of the cables or if they're symmetrical. It's basically, do I have it or do I not? Am I getting the data from that transmitter? Is it ones and zeros, and doing like a comparison between the two, if that makes sense? Again, we can't ask for the data back like a can't hit F5 on my browser and refresh it. It's a one-time shot. You got it or you don't. So with the true digital diversity with 2 antennas, if 2 antennas is good, then 4 antennas is awesome, right? So you might be aware of this, but the Axiom Digital has a mode where we can take a 4-channel receiver and put it in quadversity mode. And what we're going to do in those 8 radios, we're going to double up the radios per channel. So temporarily, I'll turn that receiver into a 2-channel receiver, and I will connect 4 antennas to it. And rather than just using like a passive or active antenna combiner system, I have a physical radio on each antenna tuned to the same frequency. So I've got 4 data streams of those ones and zeros all coming in, and the computer is making the comparison to all 4 of them and taking the best snapshot or the best picture. A good way, I was explained to me one time by people who are way smarter than me, you ever break your leg, and back in the day we had like real film on x-ray instead of the digital stuff now, and the doctor would hold it up to the light, that kind of stuff. Well, imagine taking 4 pictures of a wave at any moment in time and then laying them up to the light, and then the doctor is the computer making the decision like, oh, well, these 3 look good, but that other one didn't come out good, I'm gonna chuck that away. And that's kind of what's going on with quadversity. What the advantage is that because we don't have any combining of the different zones or the different antennas, you're getting a very clean signal from each antenna with its own separate path all the way to the hardware. So there's no chance for any phase issues. Yes?
So I guess like a real world scenario that we have actually.
Yeah.
We were using Shure and something happened, somebody tripped over our antenna tree or whatever, and our BNC popped out, so we're only working on 1 antenna. How does the system operate then? Just 1?
Okay, so the question is, what if somebody, in a real world scenario, somebody tripped over the antenna tree, and what if one of those antennas went down on a two antenna setup? So if you only have 1 antenna plugged in, or for example, if I took 1 antenna off of this little whip and I just threw the other one in my pocket, it would still work on 1 with the same caveats that we discussed with multipath before. It would be fine until there was a phase issue or a multipath reflection. And at that time, just because it would be at a 0 level, you would get nothing. So you would be more susceptible to a dropout with 1 antenna, just like an analog system. A great question. Yes?
To recap, so you said that the digital diversity model, that's just an Axiom feature, and the ULSD has like the switching feature?
Correct, yeah. So the true digital diversity is currently only on the Axient line, including the quad, the dual, and the portable. The ULSD is predictive switching. And the real easy way to tell in the Shure ecosystem is that, the blue lights that we have on top of our RF?
Oh, yeah, you're right. Yeah,
there's 2 per, each one of those indicates a radio. So on the ULSD, there's only 1 blue light, and that's it. There's not 2, right? Yes?
In a digital world, you're working in the binary domain, right? There's ones and zeros.
Mm-hmm.
So why wouldn't you just use 3 and take the best of the 3? Because before you could get 2 saying at this moment it's 0 and 2 saying at this moment it's 1, and you're getting the same sort of schism.
That's a great question. So the question for the far end is, if we're in a digital world, why are we just using 3 instead of 4? And I mean, that may be a design question, because like if you're familiar with computers, like having cluster computing, right? Like you need a quorum of at least 3, because if you have 2, they're all going to say the other guy's better, and if you have 3, at least 3, then we can really make a consensus of who's the best. I think the real reason it came down to it is the architecture, because if you have a 4-channel receiver, you have 8 radios. If you did 3 antennas, then you're kind of wasting one of the channels, right? So flipping it into the quadversity mode, which is only available on the quad, takes a 4-channel receiver with 8 radios into 2 channels. Unless you design a 6-channel receiver. But who wants a 6-channel when you have the 4-channel? Exactly. No, maybe in the future, yes. But I think the question came up with real-world scenarios, right? So where is this really being used? And I will say, it's a great feature because no matter what transmitters you own, whether or not you're using ShowLink or any of the other accessories, you can use quadversity as long as you have a quad-channel receiver. There's no other requirements except for adding 2 more antennas. You can use this to make one area way more robust. So if you're in a set and you could put 4 antennas around each corner of the room, that's one way of doing it. Another scenario would be the solution to have 2 distinct areas. Maybe you're trying to cover a set here and then a green room or a stage and a backstage area, 2 different areas. You can certainly run 2 antennas of the quadversity out in your main area and then another 2 antennas somewhere else. And that would work, in my opinion, the best, even better than using like some sort of combiner or splitting system. Again, when we're using a combining system to multi-zone, whatever the device may be, it's fine, but you definitely have more risk of introducing phase cancellations in the cable, especially if that transmitter is hitting 2 antennas at the same time. Because you got to think, it's probably going to get there a little different times, and the same problem we have with multipath, if you hit at different times, you could have a phase cancellation. Yes.
And since we're talking about quadversity and diversity, and you alluded to the combiner, is now, and we had talked about the combiner, is now a good time to talk about the combiner.
Sure. Yeah, we can talk about the combiners.
That might be, even with just a diversity system.
Yeah, we can hop there. Let's talk about the combiners a little bit. So, in the Shure realm or the traditional, when we talk about combiners, we're talking about usually intermonitors or IFBs, because we're taking a signal and we're muxing it and going out of a single point. The same thing is pretty common for multi-zone combiners. We currently don't offer any multi-zone. We only offer some of our intermonitor combiners, but there are other options out there from like the likes of PWS and WizzyCom and others, MAT288, or others that do it honestly really well. I'm not going to tell you that they don't. But it is a challenge. If you're using quadversity in a combiner setup, typically the approach would be to use like just 2 of whatever combining solutions that you would be using, or a specific quadversity type of combiner. With digital, in my experience, less is more. So I keep talking about hitting multiple antennas at the same time. You can definitely get in trouble, I'd say more so with digital, by having extra antennas than with analog. And the reason being is that we're listening for the 1s and 0s. In digital, it's not about the amount of signal, it's about the right signal. It's about, can I hear intelligently what that bit stream is? I don't care what the amplitude is, I just want to make sure I'm hearing it with clarity. So everything about a digital system is more refined, more linear, doesn't overdrive. But the downsides, I'd say, if there are any, is that when digital fails, you have nothing, right? So it's either all or nothing. There's a term engineers use called graceful degradation for analog. When analog breaks up, you hear it, you still got it, but it's not great. It's like you hear like artifacts and noises and all that crap. That doesn't happen with digital. Like, it's good, done, and then it's gone. So like a CD, it either works or it skips, if you remember CDs and such. That's kind of one of the issues. As far as covering different zones and things like that, quadversity is a very elegant way of doing it, but of course not everybody is going to have quadversity set up in your rig. Using some sort of multi-zone combiner can be a better approach, definitely. The WizzyCom devices or the PWS devices are designed for that. If at all possible, you can make sure that there's great separation between the 2 different zones. That would be welcomed, because again, if you're hitting both zoned antennas at the same time, different times they arrive, it gets a little weird, and it could be a problem. If there's any way to kind of turn a zone on or off manually and you're good with that, that would be a good way of doing it. Or a lot of people have, your tree or your cart set up where you can have your cart wherever and roll the antennas closer to the action than somewhere else. That's an elegant way of doing it. We used to offer, we kind of still do, and let's be real with you. Like the inter-monitor combiners are a way that, Shure, Sennheiser, others have designed multi-zone systems in the past. And I hesitate to recommend those solutions now, even though they technically still kind of work. And the reason being is that, for example, an inter-monitor combiner, if you have 4 channels of ears and you want to go out of a single antenna, that's a great thing to do because, and we'll cover that later, but you're taking all 4 of those signals on different frequencies and going out a single focal point with filtering and things so that the RF doesn't mix with each other. That's an awesome thing to do. But when you're using it in reverse, as far as using it to take signals from antennas, not unlike these here, which we'll talk more about, and then you're muxing them together to a single thing that's going to feed your receiver rack. The problem is that those inter-monitor combiners were designed for higher level signals. They were designed for 50, 100 milliwatts of like IFB or inter-monitor signal going out. They really weren't designed for little signals coming off of the back of a passive antenna that are like this big compared to like this big. So while it still can work, and there are systems designed out there that do it, and it's been recommended in the past, especially with the digital stuff, I kind of recommend against doing that. As much as I hate to say it, I would say you probably should look at a dedicated solution from another manufacturer, like PWS or WIZY or somebody like that, because they just do it better. And I'm not going to BS you, that's just the truth. And it all just comes down to the design. Internally, what's going on with those combiners is when we're combining high-powered IEM signals, they're knocking the power down with a big pad or attenuating it, then doing all the mixing and then boosting it back up to unity gain. So if you're taking a signal that's like super minute, like a passive RF signal, and then you're padding it down and doing your stuff and then boosting it back up, things can happen. It's going to not be as good as some other dedicated solutions. So combining, we're taking multiple sources into a signal, and with a splitter, we're taking a single one and we're splitting it out to many different ones. So we'll definitely talk more about that. We can jump around a little bit. We're going to take a break here in a couple minutes, I think around 1:15 Eastern here, just to have a drink of water and a bio break, and then we'll come back. There are many examples I have. We'll show you about different stuff as far as combining and splitting. Let's do we dive into digital now? Yes. Okay, a couple of online questions. Yeah, let's do it. Yeah.
Can you hear me now? Awesome. So there's just 2 questions online. First one comes from Nick Houston. It goes all the way back to the beginning, asking about UHF, and when you're talking about the different sizes and openings.
Yeah.
How large is a UHF wave?
That's a great question. So it's going to be a quarter wave antenna for UHF. I don't know if I have a slide on this, but a quarter wave at about 88 megahertz of VHF is going to be about the size of that quarter wave on top of a car, so about maybe a meter and a half or so. UHF wave is going to be smaller than that, so it's going to be in the few foot range, maybe 3 to 4 feet, depending on where the frequency is, and that would be the quarter wavelength size of that. So if you times that by 4, you could figure it out with the math. There are instances, mainly where a lot of things come into trouble, and I think I have some like goof slides to show later, but like putting antennas in like chain link fences and cages and things like that, which obviously you shouldn't do. That would be it. But the exact wavelength would depend on the actual frequency of the wave. But definitely quarter wave would be smaller than a meter and a half. Yeah.
Perfect. Awesome. And then our second question comes from Ken Goodwin. He's asking, when you're discussing spacing for your antennas, about a quarter-inch wavelength apart versus how close, what distance should you have between them?
I'm glad you brought that up, Ken. Thanks for the question. How far should you put your antennas? Well, the farther the better. Some people would say, well, you only need to space them apart at least a little bit, because if you have a phase cancellation going on in one, you won't have it in the other, right? Because it's a perfect 180 degrees out of phase here. So if you're even over a quarter of a wavelength, that should be fine. I mean, there's no right or wrong answer. think of it, I like to just think of it in this instance, like the farther apart the better, as long as it's going to be within, obvious practical principles, like on your cart, at least the textbook answer that Shure usually says is like 4 to 6 feet would be good. Some people will say at least a quarter wavelength, which is not wrong. But the issue with a quarter wavelength, if I put both of my antennas here a quarter wavelength away, whatever that may be, and they're both behind this pole, they're both in a bad spot if my actor is behind the pole. So you also have to think of it from a line of sight perspective as well. So it depends on the situation, but yeah, at least a quarter wavelength. Official answer is say 4 to 6 feet. The more the better, but again, realizing obstacles and what you're trying to cover to get best line of sight from each antenna, especially when using directionals towards the talent, is the way to go. The quarter wavelength is not wrong. Yes?
How does the transmission power affect all of that? Like, you've got your little contact antenna, your IFB antenna, a quarter watt, and it's too close to your other antennas. It's going to blow.
So the question came up for those on the far end, how does transmission power, if you have your contact or your IFB transmitter right next to your whatever, your wireless, what happens? Well, that's a great question. I'm really glad you brought that up. What happens is that even if the bands are different and they are separated apart, whether VHF on the contact or whatnot, a lot of times that energy is so strong that it will go right into the receiver, and what the receiver does is basically says, protect my inputs, and it'll put the pad on and it'll took everything down. You may you get kind of maybe a dropout, or you could get reduced range. So whenever you're using your IFB or contact or transmit antenna, you should keep that very far away from your receive antenna. Absolutely, the farthest possible you could possibly do. Maybe you don't have that luxury on your cart. You got 2 antennas up here for your receive, and then your contact's below. That's fine. Maybe you want to put your contact in front of your receive, so it's not blowing right back into your antennas. Do some sanity checks, like nothing on for your transmitters. Turn on your comms and see what's happening. That also brings up many cases. We deal with it all the time where everything's great, and then somebody's on a walkie and they fire it up right in front of your antenna, and boom, like all of a sudden everything goes down. You're like, all the lights come on. You're like, what happened? We were dealing with this when digital first came out with like Justin Timberlake, and they had the thrust and the campfire set up on the stage and all that stuff, and some security guy would just like heat up his walkie right in front of the antenna. So simplifying your antennas to the most basic, separating them as far as possible. You can't always control where those walkies are going to be, but if you could put them higher in the air or farther away, that's the way to go. It's called receiver blocking, is what it's called.
So then to add on to that, because we're always fighting for space with remoting our antennas with the camera guys,
yeah,
and their tear decks are very, very leaky. So it's not a matter of like what freak are you on? Oh, I'm on a 2 gig, doesn't matter. It's the power that's leaking.
It's the power. It doesn't matter what the frequency is. What it is there's so much energy. We're trying to listen to a signal that's like very, very tiny, and what we're sending out of these comms or these walkies are like 1,000 times more than that. It's crazy. So like, yeah, there's really there's filtering you can do and things of that kind of help with that, but the best case is just try to separate the transmit for receive. In the pro world, many times, like on major tours, you'll see like the 2 antennas right at monitor world, and then like the IEM antenna like right next to it. And it's because they're lazy; they don't want to like move them. But that's something in your control. If you can't control the other factors of the video stuff and the person with a 450 megahertz walkie at 4 watts or whatever, then at least you could put your antennas higher or move them farther away from the source. That's a great question. Charles.
When you're getting interference like that, is it advantageous to increase the output from your transmitter?
Correct. So the question came in, if you're getting that kind of receiver blocking from a high energy source, is it advantageous to increase the power of your transmitter? Yes, it is. But what's happening is that it's the receiver is putting a pad on all of the RF, so it's taking everything it's seeing and just moving it down, and therefore, like as a ratio, everything just goes way, way down. And if it's really bad, it'll shut it off almost completely. So it can help, but it's basically reducing your effective range of what you're trying to listen to. It's kind of like if you're at the you're trying to listen to some like real like gentle music and somebody's screaming in your ear. That's a good analogy. Like there's really not much you can do about that. Like you can try to increase the sound of that gentle music, but there's not really a lot you can do. Great questions. Yes?
How do bandpass filters factor into that whole equation?
Okay, a question on the far end. How do bandpass filters factor into that equation? I'm glad you asked. Bandpass filters are a great tool, and whether they're built into your antenna, like the WSI BFAs or LFAs, or even mini circuits or barrel filters, and there's all different kinds, they can definitely help. However, if the out-of-band emissions are so strong anyway, then it could still be affected. It really depends on the slope of the filter and how good the filter is. The main issue with filtering is that it's just a pain in the ass to retune to a new frequency, right? You got a window like blinders on a horse. You're looking at a certain slice of the spectrum. If you want to change somewhere else, now you got to think about changing that as well. So. We work with a lot of users that are using filtered antennas and such, and you taking advantage of custom groups and things. So when you're doing new frequency scans, you keep them in those blocks or those filter ranges. That can help, but it's not a cure-all. If you're in the filter range and somebody's just outside your filter range with a really high powered, in the watts, you're still gonna get affected. Yes, in the back.
I sort of a curious question when it comes to analog and digital transmission with that minimum wavelength. Does it change if it's digital or an analog transmission?
Yeah, absolutely. So we're going to take a quick break here in a minute, but we're going to cover digital RF transmission next, and we're going to talk about that. With analog, you're up to 200 kilohertz, and digital the same thing. Digital is going to use all of it almost all the time. Where analog, it'll kind of vary a little bit, but you still have to respect the 200 kilohertz spacing, and that's just the way it's been for many years. Like we talked about, it may change in the future, but right now that's the way it is. Yes.
Does analog use the full width for volume or for frequency?
Well, it's a frequency modulation thing. So analog is going to basically, the more stuff you're passing through, the more modulation it's going to do like that. If you capture at any point in time, you'll see it. But historically, analog is going to look like a tree, like a point, and then it's going to have some stuff around it. Digital, we'll take a look at the two. They're going to look like a block. It's going to be all full all the time. Analog also can pass some other signals. We talked about phase keying, where battery telemetry and stuff. You'll see that peak, and then you'll see like two little spikes on the side, which can pass other information. Like it could be like other parameters that you want to be aware of. But yeah, they do a little bit differently. But you'll definitely notice a digital signal because it's like a rectangle. Yeah. Yes.
Real quick, so I know with digital you can fit a more like a higher channel count basically into that bandwidth.
Big time.
Is that when you talk about that limited bandwidth? Is that just one unit so to speak, like one receiver, one transmitter can occupy that limited bandwidth? Okay,
so the question on the far end was digital systems can carry a lot more systems in the same amount of frequencies as analog. When we're talking about that 200 kilohertz bandwidth, is that talking about one system? And the answer is yes. That's typically, whether it was analog or digital, you're only allowed up to 200 kilohertz. If you want to use less than that, you can. But there are challenges. Not to get too far ahead, but for example, Axion Digital, 200 kilohertz, what we're allowed to use is one channel, and you can do that. The spacing allows up to 17 of those in 1.6 megahertz. So if you do the math, that's 350 space to space to space. Analog can use the same 200 kilohertz, but because of intermodulation, which we'll talk about, phantom frequencies, if you will, or harmonics, we can only put maybe 9 to 11 in one block or 1.6 megahertz. And it doesn't double if you have two next to each other. It's going to be maybe 13, not double 11, not 22. And we'll discuss that too.
Let's do the break.
All right, let's cut to the break. Very good questions, even during the break. I keep it coming. This is awesome. I want to hear about what you want to learn about and just all these cool esoteric scenarios and stuff, and geek out with the best of them. But where we left off is the digital RF transmission. When Nick came up during the break, I just wanted to share something with you. The question came up about how long is a wavelength, right? So I wasn't thinking of it, and Nick actually pointed it out. You got to think about a quarter wavelength is a quarter wave antenna. So for example, on this ADX5D, these are quarter wave antennas for UHF, right? So times 4, you're basically looking at about 4 of these would be the typical wavelength of a UHF wave. So I just figured to visually kind of connect it together. Or this is a half wave antenna, so if you doubled this would be about, I don't know, 3 feet-ish, 3 to 4 feet, depending on the frequency. So that kind of puts that question into better perspective. But now for like some more of the geek factor of the digital RF, and we understood a little bit about analog RF and why it is the way it is. Let's talk about digital and what we're doing differently, but within the same 200 kilohertz parameters, right? So a couple things we talked a little bit about. We talked about amplitude modulation. We talked about frequency modulation, the width of the slinky. AM is the height of the slinky. And phase modulation, we looked at those waves that were kind of truncated about halfway up and so forth. So again, the waves are waves. They're not analog nor digital. We're just using those waves in kind of cool and unique ways to get a digital signal over that wire. Instead of actually using that signal in its real form and listening to it, we are passing ones and zeros through that signal, much like you'd pass ones and zeros through an Ethernet cable, with an analogy. So here's a, amplitude shift keying would be a very basic way of doing this. We can either be on or off. It's digital, right? So it's a 1 is on and 0 is off. This would be what the carrier signal would look like if we're trying to throw it over RF, and that would be AM. Frequency shift keying is very similar to FM, but we are going to pass a 1 or a 0 through the frequency changes and so forth. So the digital baseband signal is either on or off, and there's the modulated carrier signal there. So phase shift keying is that kind of truncated phase anomalies there. We're going to put a 1 or a 0 through. We can use that as well. And we can combine these methods together. So why RF noise doesn't affect digital audio? Basically, there is no squelch, as we talked about. There's never going to be a blast of static through your system. The receiver is going to analyze a signal with a noise. At each time or a clock cycle, it's going to capture a picture of where that wave is, and then it's going to convert that into a bit stream signal, ones and zeros and so forth. So at its basic, what these very basic, we're not using any of these are kind of very just kind of conceptual. If we're going to see a 1 or a 0, that's what it would look like on the wave. But we're light years ahead of that, of course, in order to make this even work. So we talked a little bit about what waveforms look like. The question came up earlier. So here we are in some typical digital modulation. This is a scope looking at a kind of 2 different ways of modulating. A 2 FSK or 2 frequency shift keying would look like those little cat ears or something like that. You can see it on the scope. And then more common would be like an 8 PSK. Refer to this as like an off-the-shelf type of modulation scheme that you could use. Would look more like a typical digital rectangle, as we talked about earlier. So what we're doing, and the question came up about QAM and QAM and stuff, is that we are putting multiple bits on a single clock cycle. So at the most basic, we looked at these examples that every time the clock comes around, was that a 1, was that a 0? That's great, but that's not nearly fast enough to get real-time audio with low latency. So we have to do a little bit better than that. If we pass 2 FSK with those little ears, it's either going to be a 1 or a 0, and that's a way of doing it, but that would just be 2 different possibilities. 4 PSK would be 2 bits, so you can have 0, 0, 0, 1, 1, 1, 1, 0. So you have 4 different possibilities for 4 PSK. And then we extrapolate that to 8 PSK, while having 3 different bits or 3 different spaces that could be a 1 or a 0, all the way up to like a 16 QAM, which would, be much more advanced. So let's take a look at this in more detail. This is kind of the phase shift keying. So we have 2 possibilities of a 2 PSK of 1 bit per symbol. So basically, it either is a 0 or a 1. If it's at 0 degrees phase, it's going to be a 1. And if it's at 180 degrees out of phase, it'll be a 0. And again, this is a moment in time from the clock that captures a snapshot of this, of when it hits, where was that waveform? And we can manipulate that waveform to be one of these things, right? This is very basic, obviously just on or off at this point. If we take that waveform, and now we have 4 different possibilities, we can use 2 different points, and we can pass more data through. So we can have 4 different possibilities of 2 bits per symbol. And when we say symbol, this is these green dots that we're looking at here on the chart. So now we can pass through 4 different possibilities on that same clock cycle. 8 PSK, again, this is kind of a very common off-the-shelf. We can do in 45-degree increments, and now we have 8 different possibilities with 3 bits per symbol. And then here's a 16 QAM, which is even using even more. We're using not only phase, but we're using amplitude as well. So if we looked at this previous one, it didn't matter what the amplitude was, right? So it can be anywhere in the phase on the outside, or it doesn't matter the height of the wave. But if we combine those 2 together, now we have a 3 different layers here. We've got an inner ring, a middle ring, and an outer ring, depending on how much amplitude that wave is at that moment in time. And then we also have different areas of where it's getting caught in a snapshot. When we're doing all this, as you can see, as we get more complex and we add more what we call these constellation points, or these symbols, we can pass more data through the pipe. But we also, if you notice, it's getting a little bit more cluttered. We have to be more precise about how we do this. So one of the cool things about digital, when we made the transition from analog to digital, and a lot of users did, is that some of the other benefits came with the digital systems, not because they're magic or digital, but in order to make this stuff work, the amplifiers and the RF circuits had to be very linear. So they couldn't have distortion or an extra noise. They have to be very clean. And as a benefit from that type of cleanliness inside of the RF circuitry, we can put more channels close to each other because they don't create intermodulation and of phantom frequencies, which we'll talk about in a minute. But that's just one of the extra benefits. But it also means that things have to be more precise, concise, and on point. Like, if any of this gets messed up, you've got a dropout, right? So we're kind of like, we can get, this is 16 QAM. There are systems out there that can do like 64 QAM and stuff and get crazy, but they need a super high signal to noise ratio, and they're much more fragile. As we increase the complexity of this, it gets more fragile. So there's got to be a good balance between getting the amount of data through the pipe with it sounding good, as well as how much data we're putting through each constellation point, how fast we can do each constellation point. And there's a theoretical maximum of data and constellation points needed to get good quality audio. On the flip side of this, not only are we just passing through raw audio like this, but ourselves and every other manufacturer doing audio over digital constellation points like this is using some sort of codec to kind of compress and expand the data, not in the analog sense, but more like a zip file, like a codec. We're coding and decoding it. And how that works and how that sounds is part of the secret sauce of the different manufacturers. But if you take anything away from this, learning that it is more linear than analog because it has to be. And as we increase the complexity of the constellation points, your system has to be much more reliable and clean. Yes? I and Q. This is, I'm not sure, to be honest. This is 0 degrees phase, and this would be 270. This is amplitude, of course, as we go out. And not just conceptually, but here we're going to show what it would look like on a vector spectrum analyzer. So how it works is that, again, we're taking snapshots very quickly at certain points in time. And the computer has to make a consideration of where that amplitude, phase, and the different points. So we're stringing these along. If it's here and here and then here and here, we're putting the zeros and ones together and assembling a bit stream, and we're doing it very, very quickly. Systems, baseband audio, signal to noise, and the carrier to noise are directly related. I talked about graceful degradation earlier. Basically, as the signal gets weaker, the audio sounds crappier, and that's just the way of the beast. That's how analog works. As they go out, you start hearing fading noises and so forth, and as the signal to noise degrades, so does the carrier to noise ratio, and vice versa. So the farther the talent gets away from the cart, the signal gets lower, you start hearing artifacts and wispies, and it just doesn't sound as good as if they were like a strong signal sitting right next to you. Or you're driving your car listening to FM radio and you go out of range, it starts sounding crappy, right? Well, digital, it's like you got it or you don't. But the baseband audio, signal noise, and the CNR are not related and a lower CNR may not impact on the audio. So it's kind of a go, no-go. There's a certain amount of carrier to noise ratio that you need, and that's ultimately what it all comes down to. Carrier to noise ratio is the amount of wanted signal under the unwanted signal. As I explained, there's always noise around us at all times, and your signal is poking through that noise. And this is one of the reasons, well, not to get deep down the rabbit hole, but like why boosters just don't make everything better. When you boost, you're boosting up the wanted signal and the noise floor proportionally. You're not selectively boosting up your microphone and leaving all the noise behind. You're boosting everything together. So no matter if you shift it up or down, you're not really helping yourself out, if that makes sense. The only thing that helps you out is getting a better desired signal to undesired, which would mean higher output power, moving closer, better antenna placement. Those are things that you can affect. By putting a 20 dB booster on your antenna is not going to help any of those things. So one of the many things of why not to overboost or use boosters when you don't have to, and we'll talk about that. But again, you either got it or you don't. Analog is very good at the signal is super good, and then it just gracefully degrades into nothing. Where digital is super good and super good all the way down until it's nothing. So it's a little bit different. You got it or you don't. But all the benefits with digital just outweigh analog, in my personal opinion, by far, including density, audio quality, all of those fun things that we enjoyed today. We can also do encryption. There are some analog systems that are few and far between that can do encryption, but encryption can be done because we're dealing with a bit stream. We can actually encrypt those audio signals, and this may be useful for you in your gigs of doing sensitive information. In the touring world, it's come down to like singers that don't want their un-auto-tuned vocals leaked out to YouTube and stuff. It may be the same in the performance arena. I don't know if anybody's hanging around Steiner Studios with a Axiom digital rig, like trying to put stuff on YouTube, but they may, and the production may ask for encryption for that reason. Government, banking installations, things of that nature. With our system, there's no penalty for using it with encryption, so you can put it on and it doesn't affect anything. The only thing is that if you need to sync a transmitter, you have to physically sync it to the receiver, because that's where it shares the key over IR. You can't just tune a transmitter to the same frequency. Also, encryption doesn't really work well with the Axiom system, with like if you're doing one transmitter to multiple endpoints as well currently. So keep those things in mind, but it is possible, and thanks to digital. We talked about spectral efficiency, and we'll dig more into this coming up real shortly here. Basically, analog systems, yeah, we can put quite a few amount of frequencies in the same amount of space, but not quite like digital. The reason, in a nutshell, is that digital just behaves a lot differently due to the linear nature of its components. We talked about intermodulation, and we will talk about that. With analog, when we have two or more transmitters together, some of the energy goes down the pipe of the other one and creates distortion. We can see it here on the chart with the analog right here on the sideband. See these like little tiny, and we'll look at these more in detail, but these are created by those frequencies that are right in there. And if I happen to put another microphone frequency on one of those little frequencies, I'll have a bad time. And that's what analog does. With digital, there's none of that. It's super clean. You got that 200 kilohertz filled all the way up in that rectangle, but it keeps to itself. And therefore, I can put them right next to each other, back to back to back to back, observing minimum spacing without any issues. So that's just one of the inherent awesomenesses of digital, of why it's better, because we can pack the frequencies in tighter. As I mentioned earlier, 1.6 meg TV station, analog typically gets 8 to 11 frequencies, digital gets 17. And if I do 2 or 12 megahertz wide, I'm not getting 11 times 2 with analog, maybe getting 14. Because as I increase more frequencies, I am increasing those products that get made. And we'll look at that in more detail. With digital, it's times 2, times 3, times 4. Just as long as you're on a clean signal and there's space far enough apart from the neighbor, no problem. So the other thing too is that when analog gets together, this previous slide was showing 9 transmitters placed more than 6 feet apart. So we got them spread among the room, right? If I put these all on the table when I'm getting ready to mic up the cast here, and these are 8 inches apart. You look at all this garbage that analog makes versus digital. Digital just keeps to it, those pieces. You might be familiar or seen pictures of like award shows, and a classic trick or what they do at award shows is that, or like the Grammys, for example, they'll use bread pans, and they'll put all the transmitters in bread pans to keep this kind of phenomenon down. Maybe less so these days because it's digital. We don't have to worry about that. But what's happening is that when the energy from one of these transmitters is supposed to be going out, it's actually going into the other one and back down the pipe and causing this distortion. And that's what we're seeing here. And the closer you get together, the stronger those products are. Back to your question about people, yeah, absolutely. With 2 analog transmitters, if the talent is too close to each other, yeah, that could happen. But it's at its worst when they're all on the table together. And that's what the whole bread pan situation came to be, because like you got 50 transmitters on the table for a halftime show or whatever. You want to keep them separated. And they'll be using this at the Super Bowl and this technique and stuff. Maybe not as bad depending on how many you're miking up on a show or something, but it could definitely look like this with analog. With digital, it'll look like this. Yes?
Why is it the digital signal doesn't intermod?
Why is it that the digital signal doesn't intermod? It's because of the linearity of the components. To make that QAM and all that stuff work, it's because without the linearity of the components, we wouldn't have a great, it has to be very accurate. So from a musical perspective, it's like having a guitar amplifier that doesn't distort, like a JC120 or something super linear, like where analog would be more like a Marshall or an older amp that kind of distorts easily. And back in that day when those were made, that wasn't necessary to make analog work. So I had the extra expense of making those components linear. Intermodulation is distortion. It is more energy goes into the amplifiers, even though that these amplifiers are supposed to be sending a one-way signal out, they receive signal in, and that just puts them into bloom, and they go into that threshold where amplifiers do. The typical component, we'll get into this more, but intermodulation is when basically any nonlinear component goes into overdrive, and that would be one of these. Even though they're designed to go one way out, they overdrive. Yes?
Can we talk about brand-specific transmitters or wireless? Because like if you have a tandem unit roll up and you're using Shure,
Yep.
you don't have to worry about intermod when they're looking for frequencies. But if somebody else rolls up with something else and you want to coordinate within what they want to use, you have to worry about their intermod, right?
Okay, so the question, and I'm glad you brought this up. And the question is, if do you have to worry about brand-specific coordination if you're using Shure products and somebody rolls up with Electro or something else, right? And the answer is that yeah, we always have to worry about intermodulation from analog devices. Even if we're using digital, if I'm using, pretend that this is you or us, and somebody brings this into your set, you still can't put a digital frequency on one of these spikes because you'll have a bad day. So historically, what the proper way of doing it, if you can, is obviously be cool and make friends with the people that are bringing the gear, but you have a lot more leeway with Axion or a digital system because you can coordinate around all that stuff. You still have to coordinate your frequencies, but you can sprinkle the digital in the pockets where those aren't. The digital will never make those other things or this blooming or this other stuff that you have to worry about, but analog can affect the digital stuff in a bad way just because it is what it is. So when you fire up Workbench or most any coordination program, it's programmed to coordinate from the least agile to the most agile. So if you had like a mix of analog, whatever brand X, and Shure, it would do the analog ones first, and then it would coordinate the digitals around it because the digitals are more flexible. Oh, make sense? So I guess maybe this would be a good time to try to show you this if you haven't seen this phenomenon before. But I brought some pieces of history here, modern history. These are some Shure microphones, UR1Ms, and maybe I can, maybe I can't. We'll see. But basically, just kind of showing you this in real time with the phenomenon is of the intermodulation and how it actually is working with analog stuff. So I figure out what frequencies these are on here. These are H4 518 to 578, and basically what I'm trying to get at is showing you the intermod between the different stuff. So let's see here. This one's going to be, let's see, 557, and this one The battery doors are always a fun treat on these models here. And the battery's almost dead on these, 557 and 558. So we were talking during the break about, I got the $60 Spectrum analyzer on Amazon. We're not endorsed by them, obviously. This is a software-defined radio that is super just kind of fun to play around with. It's enough to kind of show some parameters. So if I go to preset and change the frequency center to 557, and so megahertz, and we do a span of let's see, 5 megahertz. Hopefully we can kind of see the two together react. Well, I apologize, I don't have the battery. I don't have the batteries are dead on this one. So anyway, what I was going to try to show to you guys is that when you have two of them together, the closer you put together, the more this garbage appears on the side, and you can see it in real time. I apologize, my batteries are dead. But the digital doesn't do that. There is just more linear amplifiers, more linear components, better RF check valves, if you want to call it that, isolators and stuff that make the digital work, that you don't have this problem. The other issue too, it's obvious, but in case you notice the blooming here, like the noise floor is coming up, that also means if you put any type of signal in that mess, even if it wasn't exactly on one of those spikes, your noise floor is now higher, so your wanted signal is now less than your desired, or unwanted signal is now more than your wanted signal, so you could expect poorer performance, less range, more dropouts, that kind of stuff. With that being said, I talked about Axiom Digital can do 17 and 1/6 megahertz. That's in normal mode. If you want to, there's a high density mode where you can flip it into 47 channels in that same 6 megahertz. The penalty is that you do get a little bit less output power, and we're putting the frequencies closer together. We're using a different scheme to do so. But if you had a necessary need to pack a lot of channels in a small amount of area, and far range wasn't a consideration, you can use the high density mode, which is pretty amazing. I mean, you have 47 channels in one arena. Yes? Yeah, the latency does go up. So typical latency, great question. Latency for regular Axiom Digital regular standard mode is 1.9 milliseconds. It's like 2.9 in HD. So you get an extra millisecond of latency, and the power is limited to 2 milliwatts instead of like 10 or 35 or 40. That's a great question. So digital is better. We have HD mode. We can do more systems. It's got better sound. The sound is much better. We didn't talk about that at all, but one of the test of, especially with high transient contents, or like the classic test of a digital and analog system would be like using like the key jingle test. If you put that in front of a mic, in analog systems, you hear like breakup and crackles, and that's because the compander can't react fast enough for those transients. Or another test is pretty common in the RF world, is like taking like a triangle musical instrument and going bing and letting that ring out through an analog system. It'll be like, and the digital will sound like a bell, no pun intended. So it's just a night and day. The number one thing that people will say when they come over to digital after using analog is like, whoa, all that treble. I'm like, that's all the treble you've been missing over the years, because it's just like so crazy. Some of the other benefits, maybe reduce intermodulation products, because let's talk about it. Like, we don't, in marketing, our marketing materials, we don't really tout from the rooftops like intermodulation free performance, but it is. Like, there are other manufacturers out there that do. Based on the performance of the system, it is intermodulation free. You don't have to worry about intermodulation products with digital versus analog. That's pretty much across the board because of the system design and so forth. There's some other cool things too. It's definitely more robust. There's instead of having just an RF meter on the digital systems, we have like a quality meter as well. We refer to it as Q, as you might be familiar with. And if I let me see if I can get this up here. The Q meter is more important than the audio meter. So, for example, on the system here, you can see this here. I'm on mic 3, and if you look carefully at the right here, these 5 dots, so the Q meter, that's the quality of the audio. And one thing that kind of was a groundbreaking moment from the transition to analog to digital wireless is that it's not necessarily so much important about the level of RF you're getting, it's the level of the Q meter is more important. Historically, these guys here on the the orange RF meters are quantity of how much signal you're getting. That is important, but not as important as the Q meter. For example, with a digital system, those RF meters can be really low and dancing around 1 or 2, almost in the dumps, right? But if the Q meter is still rocking 4 or 5 dots, it's going to sound just like normal, like a bell. Where analog by that point would already started getting artifacts and things. The Q is a combination of like bit error rate and the confidence that the computer inside is receiving the signal. If you're getting a low Q meter, like a 1 or a 2, it's probably letting you know there's an early warning of a dropout and that you're getting close to dropout, whether it's from interference or it's from just lack of range. The reason the Q meter is so important is picture a box like this without a Q meter. I fire up my signal, everything's working great, and then somebody that not associated with me comes in and fires up on my frequency. What is going to happen? I'm going to see full RF, but I'm going to have a dropout. I'm going to be scratching my head and going like, what? I got plenty of RF, but it's the wrong RF. It's my RF combined with theirs, mixing everything up, and now the computer doesn't know what to do. So that's why there's a Q meter or a quality meter. We call it Q. Other manufacturers may call it Q or something else, a quality meter. And at least in Axion, it's a level of 1 to 5 of the confidence of the system. In addition, digital systems have lower output power than analog because they don't need it. For example, the typical normal operating power of most digital on the table here is 10 milliwatt. They can go up to 35 or 40 or 50 in some cases. Where analog, you might be used to 30 or 50 being the normal and like 250 being, high power. Basically a 10 milliwatt digital, in my experience, outperforms a 50 milliwatt analog all day long. If you do a walk test with them side by side, it's pretty eye-opening. The lower output power of the digital beats a higher output power analog. To an extent. And that's just because of the conceptual stuff I showed you earlier with how it's not based on carrier to noise ratio. It's not the amount of signal to get the best quality. It's the right signal. It's getting those ones and zeros in the right order and understanding what they were. That's what it's all about. So that arguably is way more important. And I've seen a lot of things where it's just hanging on by like maybe almost no RF, but the blue lights are still kicking and your quality is like 4 or 5, you're in and you're good. Not to get freaked out. Like I remember way back in the day when digital first came on the scene, the meters were fluctuating wildly on the RF and people were like, whoa, I'm like having a heart attack, I'm about to get a dropout. Like, no, you're good. So just something to be aware of. Let's see.
Is there any reason you wouldn't have optimal signal to noise from the transmitter to the antenna? You got line of sight, everything's going right. Mm-hmm. Like, why would it not be, let's say, Q5?
Okay, the question for the far end is, are there any reason why there wouldn't be good signal to noise ratio between the transmitter and the antenna? What factors could play a part in that? Outside interference, of course. In the air between the antenna and the transmitter, basically outside interference or body absorption, those are like the only, or obstacles in between the antenna, those are like the only real things that can affect it. Now down after you hit the antenna, bad RF system design or not the right cable or wrong gain structure in the RF system or bad splitter implementation or wrong filters or too much boost, all of those things after it hits the antenna could be an issue. But typically for us it's going to be local interference is the biggest problem.
Can you just try to explain a little bit more about why would you have bad quality even if you had good RF, or vice versa?
Sure.
What's really kind of how does one compare to the other, and why would you lose that quality if you had good RF or
Great question. So the question for the far end is, can you explain why you would have bad quality and good RF, or vice versa, good RF and bad quality? Great question. So you could have good quality and low RF just because it's getting the right amount of data. The carrier to noise ratio is still acceptable, but even though your RF signal is low in volume or amplitude, you're getting the right signal and everything's cool. Now on the other side, you could have great RF signal and zero quality because somebody came in on your frequency, and while your transmitter is speaking on that frequency, somebody's blasting in your ear saying some other thing, and two people talking at the same time. The computer is like, I give up, and I don't know what to do.
So it's just
Competing RF could be a. That's right, or like extreme cases of like, whatever, interference from like, you're like in a metal cage, and that would also be bad RF too, but like reflections and things messing up the quality or the actual the bits or the ones and zeros going through, things affecting the phase like a lot, but typically it's going to be you're getting stomped on, or you typically, classic example, if you did your job and everything's coordinated right and you have low RF and the RF is like gone, you don't have enough to poke through the unwanted signal, then yeah, you'll have bad RF and bad quality. But if you see full RF and bad quality, the first thing to do is turn off that transmitter and take a look at that signal. Are you still seeing RF without you being on it? Then that's somebody else, and there's something else out there messing with you. Yes?
I have another question.
Okay.
Oh, sure. Yeah, just go back to the actual Axient layout.
Yeah.
So I see you have 2 meters per channel. Are those both quality meters, like one for each antenna, or is it one, like is the first one RF and the?
Okay, so from the product specific here, if we're going to talk about the Axient digital layout, the question is, what are those meters actually meaning? So in this setup, it's a standard 4-channel receiver. I've got channels 1 and 2 on. So what we're talking about here, right, these orange columns and the blue lights are per antenna. If you look closely, I don't know if I have the magnifier on here, but A and B are A and B antennas. And that indicates the blue light and Shure light. It means you have a link. It means it's happy that I can understand the ones and zeros coming from that antenna. The level of those orange meters is the level of the RF. As I get farther away, just like analog, those will go down. Now, typically on the Axient digital product, you'll see the Q meter in 4 different screens. Over here is the Q meter where you have 1 through 5, or 0 through 5, I should say. And this is just looking at mic 3. But my favorite view, I think, is typically, if we escape all the way out, you can see a couple different ones here. Like this one, you can see that little square next to the battery, hours and minutes, is Q5. But I prefer this one when I'm working is like that. So I can see all 4 channels in the queue at a glance right from here. Now there are other things in Workbench you can set up to monitor as well, but now I'm seeing all 4 channels of RF and the queue meters for all of my channels at the same time.
So the queue's always going to be on LCD?
The queue's always going to be there as well. We went back and forth, like, do we put the queue on an LED meter? Or is that too confusing? So people are used to looking at it this way. So you get both, but arguably the queue is more important than the RF. Okay. Big time. Yes?
So you mentioned something about RF performance with digital being better than analog.
Yes.
As someone who's switched from analog to digital this past year, my general perception is it's not. Like my Electro hybrid 400 series, I had great range. I didn't have to remote my fins as much.
Right.
And now in the digital system, I'm constantly doing that.
Okay.
I'm constantly putting them out. I'm also noticing that, like when I do my scans and I'm looking at RF, like it seems to me that the digital system is just more sensitive. Like it's just more sensitive, especially to nearby sources of RF or just RF in general. So like finding those clear bands of signal to work in, like, I don't know, just overall, like I personally found that I don't understand why digital isn't as good in my experience as analog as far as reliability, distance. I mean, I understand the whole thing about the quality dropping off over further distance.
There's a lot of factors that it could be. When we first came out with the digital product, you may have heard of this story, but we kind of showed it to some few select customers behind the scenes at the PlayStation, formerly the PlayStation Theater in Times Square, and we did walk tests, and we do walk tests with analog in one hand and digital with the other, and all the time the digital outperforms the analog as far as just holding on, range, sound quality, of course. Maybe some of the things, I'm not trying to make excuses, but like one of the things you might be experiencing is that the graceful degradation thing, where the analog still is there kind of, but maybe the audio is not 100% as like what the digital is going to be. You're going to get that kind of fade off, or like, the digital maybe will go out and you still get the analog a little bit, but it's not going to be as good quality as the digital. Is digital more fragile than analog? I'd say there's just differences of how it works, like the on or off aspect of it. Like you got it or you don't. If you're on a clean frequency, on the same frequency as the analog stuff, your experience should be better with the digital. But there are caveats, like I mentioned earlier, like it's not as forgiving with antenna distribution as far as hitting multiple antennas at the same time, things like that. Also, the fading out, you're not going to get a fade out. It's going to be on or off. But typically, from a performance perspective, at the output powers of like 10 versus a 50 you should probably spank the 50 with the digital in most cases, unless there's some other external factors or something at play. But I'm sorry that your experience has been like that.
Where I'm putting them out, where I put them.
So you have. Yep.
I'm pointing further. I'm pointing away from the Empire State Building. From an angle.
It's a combination. Yeah, it's a combination of that, and I hate to say it, but it's just been getting tougher out in New York, especially like in the last couple of years. It's been much tougher. But, yes.
I feel like this might be a Shure specific question,
Sure.
or just to jump off of that one.
Yeah.
What I noticed with my system, because I haven't had range issues, and it's like I don't know how many yard walk and talk on the beach, no less, and it was crystal clear. But I think a lot of Shure users are using the WYSICON antennas.
Okay. Yeah.
And there's that filter, and then there is the group selection. And so this is Shure specific, but like how do you dial that in? I think that would be a world of difference for a lot of Shure users, because that makes or breaks the system.
If you're outside the filter range, you could have issues. The WYSICON antennas are fantastic. Like they have great filters and stuff. But like I touched on it briefly, if you are doing like scans and things and you're not deploying within those ranges, or how do you deploy in those ranges? I mentioned it earlier, but like doing custom groups is really the way to go. If you can create a custom group of frequencies that's in those filter ranges, you can store up to 4 different custom groups on the receiver. And when you do a scan, you just pick the custom group, and then it's going to be in that range for that antenna. That does help out quite a bit. There's also been some craziness, like some channels in New York have been lit up without much fanfare. Like the FCC has like authorized some land mobile use for some channels, and it says it's open on the frequency finder, but it's not, and things. It's just getting tougher as well. I'm sorry, question?
So there's 2 questions from a line. First one comes from Christopher. He asked why Shure hasn't made a digital IEM system yet.
Never heard that one before. Thanks, Christopher.
Yes. He's also saying, is it inherently better to have an analog IEM versus a digital?
Yeah, let's talk about that. We talked a little bit about it. I kind of skirted around that because honestly, I hear this question. If I had $1 every time I heard this question, I'd retire already. But so the tagline, I don't know if I came up with it or somebody else, but at Shure, we're always working on new and exciting things. So I can't confirm nor deny that we're working on a digital in-ear system. So with that being said, there are digital in-ear systems on the market, but you be the judge. There has been some concerns about latency is number one, the biggest concern about digital in-ear monitors, and how it, typically 5 milliseconds for a performing artist is about average. Anything more than that starts to get a little weird. And the reason being is your bone conductivity from when you sing to your ear and the hammer and the stirrup and the anvil is instantaneous. And at 5 milliseconds, it's starting to get a little phasey. So let's chalk it up. You got 2 milliseconds on the wireless if you're using Accent. You got X amount on the digital. Let's say at least 2, and then you got yourself desk, plugins, everything else. You're approaching over 5. So it starts to get a little tricky if that's going to be good enough for some artists. Some artists can perform with 25, 30 milliseconds of delay. They're okay with that. Others cannot. They're just like, get this thing out of my ear. Also, what does it do when it breaks up? Does it fade gracefully like analog, or does it just do weird stuff? Or like, and when you're in the middle of performance, it's going to throw you off. So, those are all things that we're looking into. Will we ever come out with one? I hope so. If we did, it would probably be pretty damn cool, I bet. It would probably be pretty awesome, but as of right now, I can't confirm or deny that. But yeah, there are digital on the market, and I would anticipate other digitals trying to be in that arena. But those things you're always going to be battling. You're gonna want it all. You're gonna want the low latency, the great sound quality, the dropout-free performance, the long battery life, the small pack size. It's a lot to ask. So great question. Thanks, Chris.
Perfect. There's one more from Greg, and he's asking, is there a difference on how reflections affect analog versus digital systems?
Okay, yeah, how the reflection affects analog versus digital. The reflection, multipath reflection affects them pretty much the same. And what happens is that your reflection will basically phase cancel your signal out. So the quantity, that orange meter that we're looking at, will go down to 0 and come back. And that's normal across all wireless systems, hence why we talked about the 2 antenna approach and why we do that. So that will affect it both. I will say that reflections did affect digital wireless when they first came out, 5-7 years ago, in certain arenas and environments, buildings that are made out of metal, not unlike sound stages and large concert venues. I think there's another manufacturer was at Eurovision Sound Contest in Denmark and had issues as well because of reflections and doing weird stuff with bit error rate mitigation process and all that. So there are some other additional factors that reflections can hurt digital versus analog, but at the end of the day, reflections are bad. They're normal behavior, and we just have to find a way to mitigate around them by using diversity or quadversity. Yeah, cool. All right. Yes?
How does the receiver know to synchronize with the clock of the transmitter?
Okay, great question. So the clock of the transmitter is its own deal. So if I have a transmitter of any axis digital or digital, the clock is built in. So it's going to be doing its own thing per channel. And there's going to be a built-in clock on that signal contained within the signal, and that's how that works. Now, when we're dealing with more advanced technologies like the ADX2FD I told you, that's one of the tricks that this thing can do is because the clock is exactly the same for 2 different frequencies, we can do cool stuff by like putting the kind of assembling or doing that X-ray thing I was talking about earlier. We also have another technology that's in ULXD and Axiom Digital across the board called frequency diversity, where you can actually use 2 packs on the talent and with either 2 lavs or a Y cable on 2 different frequencies. But with this, we can't do the same thing as the combining because they're clocked differently, right? So we can use 2 different frequencies, but we have to switch between the 2. We can't assemble it because even if I did a Y cable split into each one of these packs, they're going to be clocked a little differently. They're probably going to put the 1s and 0s together slightly differently. It's not going to be the exact same picture. Unlike this, as I know it, before it even leaves this computer, it's the same. So.
Is there like a checksum or something that synchronizes the clock at the beginning of a cycle?
I'm sure there is. That's definitely beyond my pay grade. We have a complete, there's a modem development team that engineers all that, and that's part of the secret sauce. But yeah, there has to be a clock synchronizing cycle. Yeah. Cool. All right, let's move on a little bit. I think this one's very pertinent to what everybody does, because all RF systems, whether they're digital or analog, need antennas, and how you can best position your antenna for optimum use. Antennas are a transducer, so most of the antennas, especially passive ones, can either send or receive. So these little whips I have here on the back, these half wavelength whips or dipole antennas here, can be used to transmit or receive. We'll talk about polarization, but in a real nutshell, antennas like to be polarized exactly the same from the sender and pretend this is the receiver in the same plane. So this is best, this is worst. But in reality, you're going to get reflections off the wall and it's going to find itself back into this other one eventually. So there's a whole bunch of different ones, and let's kind of go down some of the ones we offer. Shure makes some natively. We also carry a line from PWS, and there are some new ones that maybe to talk about that you may not be aware of that are actually pretty cool. So from left to right here, we have the half-wave dipole that you usually get with your system. We have the UA860, AKA pipe bomb or potato masher or whatever. It's always fun going through TSA with those if you've ever done that. This over here, also affectionately called the shark fin, LPDA, a log periodic dipole array, is basically a circuit board that has basic traces on it. This particular one is an active one. We can tell by the box, and the box in the back is to make up any loss gain in the cabling and the RF plumbing. This one here is a circular polarized. This one's pretty cool. You may even have a couple of these on your cart. This is a professional wireless one, although there are some made by Sennheiser, like the A5000 CP. Same concept. Basically, it's like a helical, except we take this was clear and you can see through it, it has like a pinwheel on the table, and then we pick the pinwheel up. So it's kind of a helical, but it's a conical helical, if you will. And that has some advantages. This is your traditional helical, often seen on many carts and on tours and such. This is the 8241. They come in various frequency lengths. This one is usually passive. Professional Wireless has been doing these for quite a while. There's a new one out, which you might be interested in if you're in the market for one, called the TS, or the Touring Series helical. It looks kind of like this, except it is shorter and it's smoked. So they're much easier to pack up. As you know, these are kind of a pain in the butt to put away at the end of the day, or back on the truck or in your bag or whatever. A lot of times people use tom cases for drums to put them in. The TS Series helical is just shorter, smoked, and stacks easier in like either a case, a Pelican, or a rack drawer. So you might want to look at that. They're not totally expensive. And then more of our installed sound friends are be interested in this antenna here. This is a active wall mount antenna that looks like a Wi-Fi access point. So it's really cool to put in like a boardroom or a conference room where you need RF, but you don't want this hanging out over the very expensive chairs and conference tables situation. So this may be useful for you if you have to hide one on a set or something. You might want to think about that. You can paint the cover and make it look like an access point, maybe a hospital television show or something like that. It could come in handy. Antenna length is proportional to the wavelength. So again, the larger the wavelength, VHF frequencies are going to have larger antennas. I mentioned this one earlier, the VHF 170 to 216. You know why there's holes in it, right? So the wind doesn't blow it over. Exactly. It's like a boat paddle. You put that thing outside on a stand and a wind catches it, it's going for a ride. So that's a VHF because it's larger. And the UHF are going to be a little bit smaller, of course. We typically have quarter wave and half wave antennas. Most body packs, if they have an antenna, are going to be quarter wave. We talked about that. So 4 of these is a wavelength of what this is tuned to in the UHF range. And these whips here, these dipole whips are about this big, and those are half a wavelength tall. And these are typically shipped with all your wireless systems, and you're probably familiar with that. Speaking of half wave antennas, you got the half wave is from the top part and the bottom part, and these do not require a ground plane to work. So for example, while not best practice, you could use one of these antennas on the end of a cable. However, if you got one of the quarter wave antennas that have a BNC on it and you hung it by the cable from the grid or whatever, it's not really going to work well because it needs a ground plane or some metal to act as the other half of it. All body packs have a ground plane because they're made out of metal, or there's metal inside where the ground is connected to the antenna. So this quarter wave works with the other half of it being the metal transmitter itself. These 860 pipe bomb antenna deals here are omnidirectional. They have an element on the bottom and an element on the top, and these can be hung by the cable, which is actually really great because if you need to, again, throw one up in the grid or the lighting grid, that works really nicely, and you don't need to really have a mount for it, although we do have a mount, standard mic clip on there as well. I just explained all this, but yeah, the ground plane is required for a quarter wave antenna, and hence why some of the cringe photos we see sometimes are just quarter waves like hanging by the cable, and you're like, that's no different than just stripping off some cable and hanging the cable somewhere. It's not really doing you much good. You probably figure that out pretty quick. Omnidirectional antennas and directional are the two basic types with some similarities and differences. The omnidirectional antenna here is kind of the same as a microphone polar pattern diagram, if you've ever seen that, to kind of see what pickup it's going to be. The theoretical perfect isotropic antenna doesn't exist, but if it did, it would be a perfect sphere and it would pick up and all that. These approach that pretty regularly, and both of these, the 860 and the dipole whips like on the back of my rig here, are going to pick up from an overhead view in pretty much a kind of a circle pattern. If you look here, it looks more like a donut or a toroid or a torus pattern. Those are great. Omnidirectionals are nice antennas because they pick up in all directions, which will be more apt to catch reflections indoors. So you can kind of use them as a tool. Even though they're lower cost, they may have better performance than a directional depending on the application. But then again, directionals could be your friend, especially if you know the talent is never going to be behind you, then why waste pickup pattern behind you? So a directional antenna here has good pickup pattern from the business end on the shark fin, and then the back actually has some rejection, much like a cardioid pattern on a microphone. It's going to attenuate signals coming from the rear of it. This can be a good thing. If you're shooting on location in a skyscraper in Manhattan and there's a lot of RF coming from the window, you could use a directional antenna and point the back end towards the window, and now you're attenuating some of that RF coming in from outside and focusing on picking up from the talent. So they can be tools much like microphones. Maybe an Omni would be a good thing in one case, and maybe a directional would be a good thing in one case. If you're using a system, this question will probably come up. You might be thinking it like, can I mix and match? Like, yes, you can, with some caveats. With a digital system like Axient, yeah, you can mix and match because each antenna is treated separately. But on a predictive diversity system, maybe like ULXT or others, you may not want to do that because it may favor one more than the other. You might want to keep the two antenna lengths separate. That question comes up all the time. If I have two antennas, do I have to keep them the same? Do I have to use the same amount of cable on both sides? If I have a 30-foot run here and a 100-foot run here, do I get two 100-foot spools of cable and coil them up on the floor? Depends on the system. With predictive diversity, you might want to balance it out. With Axient or some other system where it's digital, I wouldn't hurt myself on purpose by putting a longer cable if it's not necessary, because why do that? Why shoot yourself in the foot? So that's my 2 cents on the subject, but other people may disagree. This one, the half cardioid, the 864, the Wi-Fi looking WAP antenna, this one's pretty cool because it can be mounted on the wall, painted of course. It is active, it has a booster inside if you need it, and it's just kind of invisible once it's up. It just kind of disappears. I like it. But this is much similar to a boundary microphone or a PZM or something where it's using some of the wall or the substrate to give you that half cardioid pattern. Now, helicals, this is where the fun part comes in, and why helicals are so popular is because we talked about polarization a little bit of the antennas being best on a 1-to-1 ratio, having the correct orientation, and this is bad. Well, this has no orientation because it's like a corkscrew. No matter what the talent is doing, upside down, whatever, this is more likely to catch one of those waves. It's also well used in in-ear monitors, IFBs, and that sort of thing because you can send the signal the same way as well. You might know this already, but passive antennas can be used for both in-ear monitor transmitters and receive antennas. You cannot use active antennas with boosters on them for in-ear monitors or transmitting. It just doesn't work. So this typical antenna here and the circular polarized, those are passive. I could use them for either receive or send, no problem there. And that corkscrew pattern just works wonders. Like these guys are great problem solvers. You will definitely increase your range with these over like that shark fin antenna or a dipole. But then again, there may be instances where you want those reflections. You don't know where they're going to be walking around, or you're inside of a building and you want to be able to catch as many reflections as possible. And omnidirectional, just because it's lower cost, may actually work better.
Do radials reject as well as the shark fin?
Yeah, they both. I have to look at the charts. They have a similar pattern of coverage. I don't know what the numbers are in dBu or dBi, but like -4, I guess, on the back end. As a rule of thumb, just like microphones, really, the longer the antenna, the more directional it is. And so if you have a helical with a longer spread, it's going to be much more focused than something that's shorter. Hence why this is kind of a nice balance of both. You get the corkscrew action, you get the directionality, but it's not so long that it's super like spotlight. It kind of widens out a little bit, so you get a little bit of both. And then there's also, you have to pay attention to what the frequency response. We talked about those filters, antennas and stuff, right? Most every antenna, I think they all should have either a spec chart or right on the antenna it'll tell you what they can pick up and receive or send. Most of the time, all the time I should say, it's more critical to have the right antenna on your transmitter than the receiver. Receiver antennas can be a wide range. This antenna says it can pick up 470 to 608, but other ones should be tuned to the middle frequency of the transmission capabilities of the receiver. So be careful with that if you have a bunch of different ones in different frequency ranges, that you don't mix the antennas up if they are in different frequency ranges. One nice thing about the Axient is that it is basically one range to rule them all in the US. It's G57 plus, so it's the same range for everything. You have to worry about that. But the other ones may be narrower. The different tip on the yellow antenna versus the gray, you can see the yellow one's a little longer, hence it's going to have a lower frequency than the gray tip. And as you get higher, it's going to get shorter to match that wavelength. Forward gain is included in the antenna design, so it's a fixed amount. Again, there's no electronics in this scenario, and there's different amounts of forward gain. This one here has 14 dBi of gain versus like the 805 passive, the shark fin, has 7. So this has more forward gain, but it is more directional. And we can use these figures when we're calculating out link budget or making up for losses in the RF system. Again, that's what boosters are for, is to kind of reduce any or eliminate any losses in the system, not just crank it up to 11 because it goes to 11, because that doesn't work. Boosters or active antennas are basically just a booster that's already on the antenna. In the Shure world, we currently don't have filters, but filtered antennas are cool that do have boosters. Some of them can be remote controlled even and such. This particular one can do 0, 6, or 12 dB increments, or -6 if you have too much. When would you use -6? Maybe you have no choice but being right on top of the talent, and you need to knock it down a little bit so it doesn't overload your front end. There's RF overload lights here, and then the front end of the receivers, and you'll know if you have a problem. It'll light up and let you know.
Okay, Ken had one question online, says that he is still hesitant to hide an ADX1M micro on a talent because he can't prevent the antenna from touching skin. Do you have a solution for this since it doesn't have an external antenna?
Yeah, let's talk about that. I don't know if your sales or whatever, the spiel, there's actually 4 antennas inside of here. So this ADX1M doesn't have an external antenna, much like every other transmitter on the planet. The antenna is actually internal, like inside. So it's already going to be isolated from the skin whatsoever. It has 4 antennas. The first antenna is your transmit antenna. It's a little coil here. The other 2 antennas are going to be for show link. So it's got diversity show link remote control, which is awesome. One of the reasons why people get Axient. And then the 4th antenna is the body absorption antenna, if you heard the story. So the 4th antenna, we all know that these work great out in free air, but when you put it on a bag of salt water, it doesn't work so good. So in my case, big bag of salt water. So the 4th antenna determines how well the first antenna is transmitting, and if it detects body absorption in the RF, it's a receive antenna. So if it's constantly making adjustments to the circuit for like tuning it on the fly for best performance. Now, I'm not going to sit here and lie to you and say that this is going to work better than this one, but no, this one is going to have less performance than this one for a couple of reasons. This one only goes up to 20 milliwatt, where this goes 40, and this one has an external antenna, so this one's going to get you better range, but it is bigger. So that's kind of the trade-off. If you can hide this on somebody and still get good range with the micro, then that's going to be your friend. Like people that obviously don't know anything about wireless, like I want that one because it's tiny, right? I mean, that's the deal. Like the actors are particular. So this is the way to go. But if you need the range, then something with an external antenna is always going to be better. And yes, you should isolate it from the body if possible, however you do that. But I would argue that this already has isolation because the antenna is not external, it's inside of the pack. But that doesn't say it's not immune to body absorption. If the antenna is here and I put it on my back, it's now got to go through my body, which is probably not going to do well, or reflect all the way around the room to get back. So placement is critical, especially when you're dealing with stuff that doesn't have an external antenna or lower output power. So. Cool. So we'll fly through this because we already talked about this, and a lot of this is common sense. Antenna orientation for best pickup. There's a reason why, back in the day we had set-top TVs and you put your antennas up in a V formation. A V is very much like an L. So if it's in phase this way, great. And if it's not, it'll be in phase the other way. Or you can split the difference and have it be a combination of both. So that's why 45 degrees on these antennas, or your boom box or whatever. This is the way to do it, and that's why we historically do it that way. You definitely want to avoid parallel surfaces. So these are all no-nos. Like if you put an antenna close to a wall, it's going to be bad. Why? Because it's going to reflect off the wall and come back. If you put antennas next to each other, affectionately known as an antenna farm, then that's also bad, because each one of these antennas has a significant amount of metal in it. And if the wave is coming through, it's going to be like those first slides we looked at with blocking and not fitting through those passages or reflecting off. It's going to get, it's not going to be so great. So these are pretty common sense principles, but often overlooked in a lot of applications. Transmitter to receiver antenna spacing is recommended 10 feet, and the reason mainly for this is overloading. If we are too close to the receiver, we can actually overload the receiver, putting it into protection, and then it'll pump the brakes and put the attenuators on and make everything come down and level, hurting your range for the entire system. So this is to avoid that. You use don't put it on high power really close to it, because if you do that, then it's just going to light up and give you a bad warning, I guess. I think I was doing it earlier with one of the packs that was on here. Like for example, I don't know if I can do it now, but if I go too close to the antenna, the red light pops on, just letting me know that, hey, you're overloading. Yes.
So you're saying that the antenna needs to be 10 feet from the receiver?
That's a rule of thumb.
Say if you have to be 50 feet, they put you out in the middle of nowhere.
Right. But more the better. We're talking from the antenna to the actual transmitter. What we're saying is that if you're just too close, then it's going to put the receiver into overload, is what it's going to happen. But if your cart is way out somewhere and you remote your antennas to where the action is, the same thing applies. You want to make sure the antennas aren't right next to the person. Too much of a good thing.
That doesn't usually happen. Usually it's further away.
Well, at least 10 feet.
No less than 10.
At least 10 feet, right. And that's a rule of thumb. It varies with the power. We talked about this one way early, but we'll cover it again briefly. Wavelength, like how far apart should I put them? Recommended at least one wavelength. So we had this discussion on one wavelength of UHF is around, 3 to 4 feet. So at least 3 to 4 feet would be a great recommendation. On your cart, I think that would probably be about right. But the minimum is at least a quarter wavelength away. The more the better. But then again, also pay attention to placement. If I'm behind a pole and both my antennas are there, it's common sense that if this one's bad, this one's probably going to be bad too. So a little bit more separation may be welcome for line of sight. And then we touched on this briefly as well, but you got your comms antenna, or IEM antenna in this instance. You probably should put it out front, and that because these are all directional, you are putting your energy that you're sending out in front, and these guys are going to be behind that. Now, if you put this behind it, it may be like screaming right into it. This is the best case scenario. Not only should you put this in the front, but if possible, if you could put it to the side or just separate it at all, that's going to help you out immensely. And again, you can monitor this kind of stuff by moving you move it too close, the system will probably tell you that it's overloading and you'll have an issue. So you can see that in real time by turning your transmitters off, monitoring the RF, and just see what happens while you're moving this around. Your comms antenna is lit up all the time. It's always going to be sending out energy, so you'll be able to see that energy. You won't be able to see the walkie-talkie security guy though, unfortunately. So. Put your antennas up high so you don't have to go through those big bags of salt water. That's a common recommendation, and I think most everybody's got that squared away on your cart. You put your antennas up high. Body attenuation, again, it doesn't like to go through bodies. It's one of the worst things. So if you could put the antenna somewhere where it's in line of sight to the receiver, that's ideal. If you can't, then you're probably going to be depending on reflections a lot to capture the best RF signal and not get receiver blocking. Yes?
So we spend a lot of time on location, not just like on a beautiful stage, right? A lot of times we're outside of the house and everything is in the house and we have to shoot through the house. Mm-hmm. Some houses, and I wonder if this is like a new construction versus old construction.
Yeah.
Sometimes you're shooting through a house crystal clear. Other times you're like, I have to go and remote this now on 100 feet and get right in the set. Why is that?
Well, there's a lot of factors. We were actually talking about this during the break. The construction of the house is paramount. Like if you're in like an office building or something that's using steel studs or metal studs, then there's a problem right there, right? Maybe it's a old house, this old house or something, and you got your plaster with like metal lath or something, and then you got like chain link inside of the walls. Maybe there's a bunch of pipes in the walls. It always varies. It's depending on, if it's just wood construction with like sheetrock and like insulation and spray foam, you're probably going to be okay. It may not be 100%, but it's going to be a lot more than something with a bunch of metal in all the walls, and that could happen depending on where you're at. So the question, I guess it does vary. The only real way to know is to test it. Set up your rig and do a walk test outside. If you're using the Shure gear, you could use the timeline function where you record and go outside and come back, and then you can look and see what happened with your RF and stuff. So, yes, question.
We have another one from Christopher. He says, if the AD receivers do filters per receiver, or if there's a shared filter for the entire front end.
So yeah, there's filters for the whole range. As it's designed, the system is wideband from 470 to 608 in the US. So there's a filter for that whole range. You don't have to pick and choose where you put your window. Some systems you do have to pick a window of 24 or 40 megahertz or whatever. You could put one at 470 and one at 608, and that doesn't change. So the filters are for the unit. Could you use external filters? Absolutely, if you want to. Whatever type on the antenna or barrel, you could do that. But as far as the hardware's action is concerned, the filters are the top and the bottom of the range. Yes?
When you have a directional antenna and there's a Empire State Building,
yes.
How much is the degree of how much you want to reflect compared to a directional microphone? If you put it 180 degrees, you still pick it up?
Yes, you still can pick it up. With a directional antenna, it will be less if, the question for the far end is what's the kind of the range of a directional antenna if you got a strong source like Empire State Building or a bunch of TV transmitters? What's your angle? It varies on the antenna. They're in the spec sheets of the antenna, so if you're interested in a particular one, they're usually around 75 to 90 degrees, but each antenna is a little different. If you look at each antenna will have a spec sheet showing you that angle. But will you still receive some stuff if you put the back end to the window? Yeah, probably because of reflections, you'll still get it, but it won't be as bad as if you were pointing directly at it or using an Omni, yeah.
We have a film location, somebody's in the car, we're doing a handheld 360 degrees, you cannot put your antennas anywhere. You guys go around the block because we're doing another walk and talk, so you have this tiny little place to put one antenna, hopefully two if you have two in your carts. Do you try to both put them still as directional in your linear, like trying to aim to the place of your transmitter, or are you trying to aim your directional antennas to try to find the bouncing ones?
Great question. So if you're outside, question for the far end, if you're outside, are you using directional or omnidirectional antennas, and what's your kind of game plan for capturing action that may be in one space or the other? You may only have one chance to set up for it. It should be known that directional antennas work better outside. The reason being is that there are minimal reflections. If you're on a beach or outside in the street, you're not going to have the walls helping you out to keep the RF inside. So directional antennas do work better outside for that. There's less stuff to bounce around. However, they are directional, so you do have to point them at the action. If you have an opportunity to use directionals and you can adjust them between takes or whatever and shoot and move them where you are, then maybe an approach.
When you're having two antennas behind the pillar, they're both going to suck because of the pillar. So how do you solve that? I mean, by trying to move your antennas away from the pillar, I presume, but would it be smart to have one be directionally in a different place too?
As long as would it be smart to kind of separate your antennas to cover the two different areas? Yes and no. I would encourage you to still try to maintain the diversity, because if you only have one antenna that's actually doing the heavy lifting on that scene A, then if you get a phase cancellation for whatever reason, you have a dropout. So you've got to at least have some sort of two antennas being picked up in range at all times, the first parameter. If you want to separate them and kind of split thirds or cover the two different areas, then yes, that would be fine. But I would hesitate to recommend just using one antenna really close and the other one's not even really picking up, because that could be a problem, just based on multipath and having phase cancellation. A good question. Yeah, I mean, those are real world scenarios, you know? Yes?
So the beach, are we ever going to beat the beach, or is it just science and like it's going to be a signal suck no matter what?
Signal sucks no matter what because of the beach and the uneven terrain. However, water, if you ever shoots over water, can go quite far because the water, it can skip and bounce over the water. So the best bet, higher antennas, directional antennas pointed right where you can. The highest power you can do on your packs and transmitters. Those are really the things that you can do besides moving closer to the action. But yeah, that's a tough one. Not much to bounce off of on the beach, and a lot of things to catch the signal and put it into and stop it. It's not going to bounce. It hits the sand. It's going to kind of get sucked up. But you know, higher and direct line of sight, the best you can do. Yeah. Yes.
Yeah. So I was on a gig a little while ago, and they used two Shure shark fin antennas. Right. One was in disorientation. The other one was like right on it. Like,
sure.
And he was like, "Oh yeah, that's how you're actually supposed to set them up." But that sounds like it's wrong from what you're saying. I'm not saying it.
I'm not going to say it's wrong. You know, you ask 10 different engineers, get 10 different answers or 10 different users, that kind of thing. It's not wrong. There are some, like there's some antennas on the market that do have that built in, because I think it's the 90 degree. Is that any different than doing the V on 45? Not really. Is it a bad thing to do? I don't think it's a bad thing. You're kind of emulating a circular polarized because you get the 90, and then the 270. I think that's okay. Or in my opinion, it's no different than doing 2 on a V. Like it really is. It's the same. It's an L just on its side, right? So.
You had them like right up on each other too, so they should also be spread out.
I would encourage, no matter what you're doing with the orientation and the polarization, I would definitely spread them out. Yeah. What we say, 4 feet or better, or at least a wavelength at the minimum. More the better, in my opinion. You can't always do that, but. Yeah. Yes.
Do you use Yagis ever?
Do we use Yagis ever? It has been done, but the issue with the Yagi is it's super directional, right? So like if you got a
good in situations of like the beach.
If your talent is in the same spot, yes. If you have to track them, then now you got somebody kind of like booming with your antenna, like trying to get it right. And so there's pros and cons of both. Typically, the Yagis in professional applications would be like point-to-point stuff. Maybe you got a real far thing at the presidential inauguration and you got to do tower to tower. Directional antennas may not be best. They're not moving, so I can point a very pinpointed antenna at where I need to send or receive. So Yagis do come into play, but not as often as all the other types. The ones we covered today are really the lion's share of it. Yagis, I would say less than 1% or 2% of applications. Yeah, great question. Yes?
So the ankle's a common placement area for radio. So in that instance, would a lower antenna placement be beneficial?
I would say no, because like you're still got all the things blocking you in the way. Putting your antenna lower to the ground is just going to be worse performance than putting it up. Unless you're like happen to be right there or something, I would still argue that you would be now more likely to be facing other challenges, bouncing off the ground. And anytime you put your antennas up, you're going to get better reception. There's a reason why transmit radio and TV towers are super high on mountains, is because of better propagation. Yeah.
They can be advantageous because there's less meat down there.
Yeah.
I like it. Charlie, less meat to go through. Yeah, if you can get there, sure.
Yeah, so then the question would it be oftentimes, the back is small in the back, so it's shooting through the actor's body.
Yeah.
What's going to be better, the small in the back or the ankle?
I'd say the ankle.
Ankle, right? Yeah. Less meat.
Yeah.
Cool. Any other questions? We got a couple minutes here. I can show you some of the new stuff if you want to.
Let's see some new stuff.
Want to see it? All right. Has anybody seen the 8600 or the new Spectrum Manager yet?
Nope.
All right. Let's take a look. All right. So if you haven't seen this is pretty cool. I'll go through it. It's not super complicated, which is nice. Okay. So here we go. In this little portable rack setup I have an Axiom Digital quad at the top in regular mode, the AD600 Spectrum Manager, the SBRC rack charger, and then a PSM 1000 transmitter at the bottom. The Spectrum Manager is like the predecessor, except it's newer, better, cooler, faster, all of that stuff. instead of having a sweep from low to high, it's real time. So if something just pops up, it just shows up. There's no more scanning. Like, so it's that. It also lets you set up your systems without a computer. Think of it as Workbench in a box. So we try to do that like the, if you're old enough to remember the Clippy from Microsoft Word, like it looks like you're trying to coordinate some frequencies. Like it does that too, and I'll show you that as well. It can do advanced, and so if you don't have room for a laptop or an iPad, you don't want to use that, this is actually pretty cool. In addition to that, it does what its predecessor did. It stores your backup frequencies for Axiom Digital. So if you're using the automatic frequency interference and avoidance, or frequency hopping, what everybody calls it, this device stores those backup frequencies. But I really like to show how cool and easy it is to set up. So like if you're getting onto your set here, you can go right to the menu, and there are only 5 options, so it's not super complicated. You go to frequency coordination, and I say, okay. 4 options, you can either create or update, or create or update advanced. We'll just do create a new coordination from scratch, basic. It knows all your network devices, so it saw the 84Q right here, and it knows that. If you had more than one, they would show up. If you have portables like the ADX5D, those would show up as well. And you hit, okay, we found those. Turn off all your transmitters and do a scan. And this is probably old hat for basically everybody. Let's do a scan. But instead of waiting, it's going to go, done, and that's it. We're done. So it did a scan like in less than like, I don't know, a second or two. That's good. We'll stop the scan. And these are what's happening here. It's obviously pretty polluted. And we can go next. And it's automatically going to calculate out our regular frequencies and backups. So we asked it for 4, which is obviously trivial, but it's going to do 8 backup frequencies as well. And then you just hit next, deploy. Are you sure? Yeah. And if you notice, my channels 1 and 2 are linked up. And if I hit this deploy button, we just sent the frequencies out, and channels 1 and 2 are still kicking because of the magic of ShowLink. Yes?
So Workbench, you could plug in, like I've got my contacts, I've got my Electro IFB. Is there a place to plug that in on this?
Oh yes, so you can do that if you want to with the advanced coordination. I'll show you that. It's more tedious, of course, because it's a big screen, but you still have to work the knob here. But if you do create a new coordination advanced, it's the same thing, but it gives you a lot more stuff, right? So I know it's hard to see here, but it says like, frequency requests, you can put other things in. You can do exclusions if you have a certain range you want to stay out of, like Workbench, you can do that as well. You can do advanced options by changing the order, or analyze a new list, or use a user group and all that, and calculate. So it does add those facilities like Workbench does from the front panel. So if you know you want to stay out of the public safety and all that, you can do that with this without a computer. It also has a USB port in the back, so you can not only charge your phone, but you can like import and everybody asks that. You can import and export your coordinations and things like that through Workbench and vice versa. The back of the hardware actually has the same 4-port switch that Axiom Digital does. So you have 3 network interface cards. It has Dante, so you can use it as another Dante listening source. It has 6 antenna inputs instead of 2. Now, it doesn't have the daisy chain option like the predecessor did, but with the 6 inputs, you can do different frequency ranges. So what's mind-blowing about this is that, if you are using a combination of UHF, VHF, et cetera, you can kind of go here and specify what those are going to be. If I go into the menu.
You said inputs.
Inputs, yes.
Move out.
No, it does no loop out, but you have 6. So a lot of people asked about, hey, what do I do about quadversity? How do I monitor all 4 antennas? Well, you have 6 inputs. You can use them individually, or you can gang them like VHF, UHF 1.4, or VHF, UHF 900 megahertz, or main stage, outside, green room. On the same frequency. It's up to you. So you can specify what frequency ranges those want to be, and then you get to look at them at all times. There's no scanning. It just shows up right on the front screen. So, yeah, a question?
Since you can't daisy chain, if you lose power to your spectrum analyzer, does that mean that your racks aren't going to work anymore?
No. So this would be like more at the bottom. Like you would already since you can't daisy chain, you'd either daisy chain it underneath an Axiom Digital already, or you have an antenna distro that you're already splitting to, and then you feed this like another receiver, basically at the bottom of the chain. So if it went dead, it wouldn't matter. Not that it would. it does have a DC powering option as well, which everybody wanted for the other one that did not. So this one has the same DC XLR input as just like you would get on the option as the Axient. You can power it off your car battery. Yeah. Yes.
I'm assuming this device negotiates the Zigbee network as well?
No, so it doesn't negotiate the Zigbee network as far it's part of the ecosystem, but you still need the access point, the 8600, to do the communication.
Gotcha, but as far as frequency coordination for that, is it doing any of the heavy lifting, or is that all happening in the 600?
No, that's still all happening like legacy, like the like it does. You can use the 8600 to view that Zigbee action through Workbench, and you can do that. But it's not coordinating any of that. It's just coordinating your normal frequencies you'd use.
Most congested part of all of this.
Right, exactly. In a like a real dense Zigbee network environment. Yeah, absolutely. Yes.
Christopher asked if you can explain the two Dante transmit channels on the 8600. Receivers is part of the ability to drop and listen to other channels, but what about the transmits?
Right, so it does have Dante built in, primary and redundant. You just like Axient, you can pick off anything off the Dante network and listen to it, which is cool. I'm pretty sure that you can send the listening output of whatever you're listening to out the Dante, I'm pretty sure. And it also has like the listening port. If you see any spike, you can listen to it as long as it's analog or Axient digital, not encrypted. So if you see something out there and you don't know what it is, you can tune to it like the old one, put your cursor right on it and say send it through the headphones and listen to what that is. And that's it could be helpful. It'll be like, all right, well that's so-and-so with the X brand or whatever. But currently right now it only does analog and Axient digital. Cool. So like, I mean, the basic, the whole thing is on the top here. You have antennas A through F, and you can turn each one off or toggle them on or off if you wish, which is cool. But you have your scan tools, and just like a spectrum analyzer, you can zoom in on a certain range, right, and see what's going on. And if I want to, I can listen to it, put my thing over the spike there. And then the main menu itself, I guess what I was talking about earlier, to show you the, a couple other things. It has a real-time clock. So there's a battery in it, and it remembers the time and the date, which is important. It can also do event logging. So the age-old thing, like, well, what happened, right? Well, this can keep that event log if there was a problem, and let you see, just like Workbench, and give you a real detailed list of that, and timestamp it. So if I knew I had a dropout at 3:15, then I would, basically have a record of that time-stamped. You can import and export that as well. That's a new addition, and then. The antennas here is pretty cool. This is what I was talking about. You can either gang each pair together or treat them separately for whatever frequency range you want. It's hard to see, but this is showing you, it's a VHF or UHF or 900 megahertz or 1.4 or whatever you may be using all together. So it does all that, and what the old stuff did, but quicker, faster, prettier display, DC powered, which everybody's been asking for. So we're psyched about that. That's it. Any questions on the far end, or we good?
Great. Okay.
More new stuff.
Okay, well, why don't we wrap it up here in terms of that? And if you want to come see more new stuff, Ben will be here for a little bit. Ben, thank you so much.
Thanks for having me. I appreciate it.